It's already, yeah, linked to the YouTube. Yeah.
Yeah, I'm starting the YouTube now. Yeah. Yeah, I'm starting the YouTube.
Professor Kobeda also already joined us.
I don't think so now, but I contacted him yesterday and just to be sure that he was attending. So I asked him to join sometimes before the starting of his lecture. So I don't know because he has also clinical duties. So it depends on.
God should confirm the Zoom. Yeah, Zoom link. Okay. How about Tencent also? Link? Already linked? Tencent?
Oh, it started a different link.
Oh.
I don't know why, but it started in a different link, the YouTube. Why, but it started in a different link, the YouTube. Nick, I think that, well, there has been some issue with the live streaming in YouTube because for some reason it started with a new YouTube link.
But the attendees can know this new one.
So what I'm going to do is I'm going to probably paste a comment in the old
Yeah.
YouTube link. linking it to the new one.
But at first, should link to the YouTube and then Quai link to the Tencent. Right?
Yeah, so I have just provided the link to
That,
Quai, the new one.
Yeah, but Tencent, the link is don't change. Yeah.
So I don't know. I don't know. Maybe the Tencent link also will have to be adapted.
Yeah.
So let's see if Hongzi can set it up.
Eh, 他如果是换了一个 YouTube 的号，然后你的 Tencent 告诉你了，你的 Tencent 的号可以不变吗？不用变哈。对，那就好，那就好。但是问题是，他现在 YouTube 还没上去呢。Yeah, I already confirmed with Quai. If you use the new YouTube link,
Yeah.
but Quai use the same Tencent link.
Okay, so I have pasted the
Just,
new link, YouTube link here in the chat. So can Quai please take a look at it and connect it to the Tencent?
Yeah, also using the same Tencent.
Yeah.
Link number.
Okay.
Yeah. If you use the new YouTube link, and Quai use the same Tencent link.
Okay, so I have pasted the new link, YouTube link here in the chat. So can Quai please take a look at it and connect it to the Tencent?
Yeah.
Okay, it works.
Using the same.
Okay, Hongzi, thank you.
Tencent is okay. Yeah.
Okay.
If you, but how to announce about this new YouTube link to the attendance? Maybe announce at our homepage, website.
Yes.
Website. Oh, yeah.
Yes, it has been updated also in the website. So there is the new link which is posted in the website.
Mufti, I
Yes,
suggest to
start. Yeah.
Yeah,
Yes, yes. So, well, we are almost there. So as everything is now there, please, Ning, I think that, well, we can start. Yeah.
Okay, we start now. Okay.
Yes, please. So I'm recording the meeting.
Okay. Okay, it's the time to start our opening ceremony. Ladies, gentlemen, colleagues, and friends, welcome to Brain Informatics 2021 virtual conference. My name is Ning Zhong, serve as a co-chair of Brain Informatics 2021 committee with Mufti Mohammad Safno, personally, Chunghai Dai, M. Shan, Kaiser, and Yang Yang together. I'm also the steering committee chair of this Brain Informatics conference series. First, I would like to share a video with you, introduction to the Brain Informatics conference series. Okay, thank you for your watching. From this video, you can see the Brain Informatics Conference Series has established itself as a world premier research forum on brain informatics with a key theme, brain science with artificial intelligence, which is an emerging interdisciplinary and multidisciplinary research field with joint efforts from the neuroscience, cognitive science, medicine and life sciences, data science, computational science, artificial intelligence, neuroimaging technologies, and information and communication technologies. As you know, we originally planned to organize this year Brain Informatics Conference in Padua, Italy. Due to the coronavirus pandemic, we decided this year conference is also converted to a full virtual conference. So next year, Brain Informatics 2022 will take place physically in Padua, Italy, as one of events of celebrating the University of Padua 800 years anniversary. And the next year, conference will be co-hosted by University of Padua and the University of Queensland, Australia, and co-located with WCCI, the IEEE World Congress on Computational Intelligence in July 15 to 17, 2022. I hope you all are doing well in this challenging time. Thank you all very much for your strong support, contribution, participation. Enjoy this conference. So next, I would like to invite Professor Stefano Bastianini to give the opening address and more information about Padua, Italy. Please, Professor Stefano Bastianini.
Thank you very much, Professor Zong. It is, of course, a privilege for me to introduce the conference on behalf of the University of Padua. So I have a few slides. So I remember last year, we were all hoping to have this meeting in person. And unfortunately, we are yet here again virtually. So I just prepared a few slides to show you Padua, our university in brief, and let's say pretend to or ask you to image if you were really here in person. So let me share my little presentation. So first of all, Padua is a city located very close to Venice, 30 kilometers from Venice in the northeast of Italy. The city of Padua is a very pleasant city and with a very nice historical center. Also, it is not as famous as Venice. It has definitely its own beauties. This is Prato della Valle, one of the biggest squares in Italy. In the context, I would say, of an academic conference, it is important to remember that Padua has different jewels in terms of cultural heritage. Particularly, I would like to highlight two jewels that are listed within the World Heritage List of UNESCO. One is the Botanical Garden. It is linked to the university. Actually, it was funded by the university. It was let's say it started the history of the Botanical Garden in the 16th century, and it was built by basically with the support of the Republic of Venice to teach medical students how to recognize medical plants and to avoid, of course, to prevent mistakes and frauds. And it is still there. It is a very nice place where to go for a visit, to maybe also to study. And of course, let's say, I hope you will see it live next year. The second very important jewel again in the list of UNESCO is the cycle of 14th century frescoes. The most famous of these frescoes in the chapel of Scrovegni, also known as Madonna dell'Arena. It is a beautiful, outstanding example of Giotto paintings of the 14th century and representing the life of the Virgin and Christ. So people are coming here from the whole world to admire these paintings that were essentially also in the history of the painting were very important because they introduced for the first time the perspective. Yeah. So Padua is also a very lively town. It is full of markets where you can appreciate Italian food and fresh food and the food of the Italian tradition. This is, by the way, in the background, another jewel. This is called the Palace of the Reason, literal translation from Italy, Palace of the Mind, I would say. Yeah? It was where the governing body of the city was located. And I think it relates somehow with this conference because, again, it is the site where the brain was believed to be in the city. The brain, of course, the governing body of the city, as it should be, of course. Okay, few words about the Padua University. This is the third oldest university in Europe. It was founded in 1222, and next year will be the 800th anniversary. It is a very nice, a very important point is that it was funded by students. Students paid their teachers, were choosing their teachers, and it was a bottom-up university aimed at the freedom of thinking. Over the years, the university has grown in importance, and very famous academics were teaching here. Among them, for example, Galileo or Copernicus, as well as anatomist Vesalio and many others. So there are traces, of course, of these people remaining yet in the university, and the chair of Italy where Galileo was teaching still there, or a very nice anatomical theater that you will admire when you will be here next year. So a final mention coming to nowadays. So concerning particularly this conference, we have recently established here a center, an interdisciplinary center that covers brain research, starting from, let's say, clinical aspects and going down to animal models, experimental models, and theory of the brain, including, of course, brain informatics, which plays a very important role in this interdisciplinary approach to the brain. So also it is at its infancy. It is, of course, directed by Professor Corbetta, who will give a keynote lecture later on this morning. And so you will be welcome to visit us at the Padua Neuroscience Center, and hopefully this will also serve to establish future collaborations. So I really thank you for your attention, and I give the floor, the virtual floor, to Mufti Mahmoud, who will instruct you about technical things of the conference.
Thank you very much. And well, at this stage, we are running slightly behind the schedule, roughly like by 5 minutes. So allow me to very quickly introduce the technical program that we have for the coming 3 days. So the conference, as you know, is 3 days long. So starting today is the first day of the conference, and then there will be the 2 more days to come. So tomorrow and the day after tomorrow. So I hope you can see the screen, okay, that I'm presenting. So here I'm going to just summarize the key information, what to look for the next 3 days. So it's going to be vibrant and busy 3 days, okay? All times are in UK local times. So I would like to again let you know that, well, all the times that you'd see are mainly in UK local times. And then we will start on day 1, which is today. We started at 8:30, and today we will stop at 4 p.m. UK time. Day 2 will start at 9 o'clock in the morning, and then we'll stop at 4 p.m. And then day 3 will start at 9 o'clock in the morning, again UK time, and end at 12:30. So the complete program will consist of 8 keynote speeches from very prominent scientists, then 11 workshops, 3 special sessions, 50 technical papers being presented, and 18 abstracts will be presented. So it is going to be quite a busy schedule. So there will be parallel sessions. However, the keynotes in all the 3 days will be serial. So nothing parallel is going to take place there. Can I just request maybe some of the co-hosts to take care of the attendees who are joining in, maybe? So the day 1, day 2, and day 3 parallel, the serial sessions will always take place through this Zoom link that you can see here. This is also something which is available in the conference website. Just to click and join. At the same time, I would like to bring your notice that, well, this program is live telecasted through YouTube and Tencent for the people who cannot have access to YouTube. So, well, we are expecting around several thousand of people probably is joining with us virtually today. So there are parallel workshops and sessions once the keynotes are over. So there will be parallel workshops and sessions. Though I am going to give a very brief account of each of these workshops and sessions later on, but well, this is something I would request you to refer to the conference website for detailed information regarding the presentations that are going to take place in each of those sessions. And then, of course, at day 3, there will be parallel technical sessions covering the 5 themes of the conference. So the first keynote for the day would be by Professor Mauricio Corbetta, and he will be talking about toward a computational model for brains affected by stroke with an eye to their repair. So which is going to start immediately after this opening session ends. This is something which will be followed by the second keynote by Professor Stefano Panseri, who will be talking about neural circuits, their interactions, and local field potentials and electroencephalogram measures. And this is something which will have a brief break. And then we will again move to the next keynote, which will be provided by Professor Wolfram Gressner, and he will be talking about Hebbian plasticity rules. Followed by this would be the fourth keynote of the day by Professor Tianzi Xiang, and he will be talking about the grand challenges in brain health with artificial intelligence, mostly how China is tackling to handle the situation overall. This is something which concludes the day 1 keynotes. There will be 4 keynotes in day 1, and then there will be 2 more keynotes. sorry, there will be 4 more keynotes in day 2. So day 2, the keynote number 5 will be delivered by Professor Nikola Kasabov, and he'll be talking about brain-inspired brain informatics, its methods, systems, and applications. Then this is something which will be followed by yet another keynote by Professor Jianguang Yu, and who will be talking about the essential tremor detection and assessment using machine learning from wearable devices. So followed by yet another keynote by Professor Simon Eckhoff, and he'll be talking about from areas to networks to individual predictions. Unfortunately, due to a urgent family problem, he will not be able to be present in person during the session, but we have his recorded video to play during the session. And finally, the last keynote will be delivered by Professor Partha Mitra, and he will be talking about mapping circuit architectures and mammalian brains at mesoscopic scale. And this is something which would conclude the keynote sessions. And well, after the keynote session in the day 1, we will have parallel workshops and sessions running. So there will be a workshop which tries to focus on AI-driven tools for inclusive and personalized education for students with learning disabilities, focusing on autism. And then at the same time, there will also be another parallel workshop focusing on human-computer interactions and cutting-edge technologies, how psychology and other things are playing part in there. And then yet another workshop would be on computational neuroaesthetics, okay? Followed by another one which will be computational intelligence in healthcare. And then we would have the workshop on internet adoption and mental health. Then there will be methods and technologies in brain imaging. So this is something which marks the end of day 1's workshops, so workshop and special sessions. And in day 2, we have yet a number of very interesting workshops, starting with the emotion recognition workshop. And in parallel, there will be computational brain image analysis and genomics. And then we'll have web intelligence meets brain informatics and computational intelligence methods in processing and analysis of neuronal big data. And there will be one special session which will be explainable artificial intelligence for unveiling the brain from black box to glass box. So this is something which concludes the special sessions and workshops on day 2. And on day 3, we have one workshop which is due to the difficulty in the different time zones. Well, it is organized in a very difficult time for the European counterparts. But well, people who are joining us from America and from Asia will probably be able to still enjoy the workshop. It's a very nice one. It talks about cognitive neuroscience of thinking and reasoning, a very nice one. So this is something it is followed by the parallel technical sessions. So we have, as a part of the conference team, we have 5 parallel sessions or 5 tracks. The first track is the cognitive and computational foundations of brain science. So the number of contributed papers and abstracts will be presented here. And then the parallel technical session 2 will be focusing on investigations of human information processing systems. And then parallel session 3 will be focusing on brain big data analytics, curation, and management. This will be followed by parallel technical session 4, informatics paradigms for brain and mental health research. And finally, there will be the parallel technical session 5 with the topic brain machine intelligence and brain inspired computing. So the links to each of these sessions are embedded in the program which has been shared through the website. So please do refer to the website, download the program, and discard any of the previously communicated programs that you had before yesterday, because we identified an error in the meeting link. So please, if you had downloaded the program before yesterday, please discard that program and re-download the programs from the website. Thank you. And finally, we will have the closing session, which is going to be on Sunday at 11:30, between 11:30 and 12:30. So during the closing session, there will be the best paper and other paper awards and the announcement for the next 2022 conference. And with all of these, I would like to welcome you all to this particular to this conference, and I hope that you will be enjoying the sessions with us over the next 3 days. So welcome again, and back to Professor Ning Zung.
Please, Kate. Yeah. Okay, let's start the first keynote talk session of this conference. Yeah. Yeah, welcome again to join this first keynote talk session. My name is Ning Zhong, serve as this session chair. It's my pleasure to introduce our keynote speaker, Professor Kobeta, who is a former Norwegian staff professor of neurology and professor of radiology, anatomy, and neurobiology and bioengineering at the Washington University School of Medicine. From 2001 to 2016, he was chief of the division of the neurorehabilitation and the director of the neurological rehabilitation at Washington University. As of October 2016, Dr. Kobeta is full professor and chair of the neurology in the Department of Neuroscience at the University of Padua, Italy. He is also the founding director of the Padua Neuroscience Center. Professor Kobeta has pioneered experiments on the neural mechanism of the human attention using PET and functional MRI. He has discovered two brain networks dedicated to the attention control and developed a brain model of attention that has been cited in the literature more than 11,000 times. His clinical work has focused on how focal brain lesions affect brain physiology and network organization. In the last 10 years, he has studied the network-wide effects of the focal lesions, their efforts on the behavior and recovery, and their modeling through whole brain models with air to the neural modulation. His research has been recognized with several awards, including the highly cited researches by Zams based on the top 1% rate of the citation in the last decade. So the title of his talk today is Towards a Computational Model of Brain Effects by Torque with Air to their Repair. So let's welcome Professor Kobeta to give us this really exciting talk. Yeah, please, Professor Kobeta.
Yes, good morning. Thank you, Professor Zong. Thank you to the organizer for inviting me. I'm very excited to be here, and I really hope that we're going to have a chance to meet in person in Padua the next time. So let me share my screen. Can you see it? Can you see the screen?
Yes, yes, it's visible. Yeah.
Okay. So what I'd like to do today is to give you an overview of work that we have done over the last 10 years. And I believe that some of this work is kind of a good paradigm for the kind of information that you need in order to build a computational model that can mimic normal behavior and at the same time potentially can be modulated for taking care of pathological conditions. There are some kind of basic sets of information that we need. And so I think we are building up kind of the features that are necessary for building a model. Now, the model, we're just beginning, but I'm going to discuss some of our experiments towards doing that. So this is the outline of my talk. And I think there are two kind of main messages that I'd like you to take home. The first one, you will see that stroke are a very heterogeneous condition. I think most of you believe that different people are affected in different ways by having a stroke. And therefore, the behavioral deficits are very different from person to person. And similarly, the brain mechanism may be very different from person to person. But what I'll try to show you that there is a great deal of low dimensionality, both in terms of behavioral deficits as well as brain mechanism, which is, I think, very good news if someone has an eye towards repair and rehabilitation. The second take-home message is that the dynamics of the system, of course, are very important, although they've been understudied. And we're just kind of beginning, after studying for many years the static mechanism, now we're beginning to study some of the dynamic mechanism. And one main point is that I think is going to be key to model not just the cortex, but also model the subcortical-cortical interaction, because we see that these interactions are very important. All right, so what is a stroke? A stroke, there are two kinds of strokes. 80% of the stroke is basically an obstruction of blood flow to an area of the brain. The brain at value from the obstruction dies very quickly within 4 minutes. You have loss of pumps, you have loss of potentials, resting potentials, and within a few days, that area is completely dead. There is also an hemorrhagic kind in which you have basically a rupture of a blood vessel, and that also causes through ischemia, as well as pressure, as well as excitotoxicity, causes neuronal death and glial death in a specific part of the brain. Now, from this illustration that comes from Netter, which is one of the kind of the best illustrators in the world of neuroscience, you see that the emphasis, and I think this is the gestalt that we have also if you Google stroke on YouTube or on Google, you will see that the gestalt is that stroke is a problem of the cortex, is a problem of neuronal modules that have been damaged. And I think another take-home message today is that I think, and I will demonstrate, the stroke is a problem of connectivity of white matter cables that are affected by the lesion, and there is a problem of communication between cortical areas. So before we start, I want to give you a sense of the specificity of some of the patients, some of the deficits that we see. This is kind of a straw man, because at the end of this, I will tell you that there is a lot of commonalities across patients. But this is a patient that resembled the one that was described in 1861 by Paul Broca, and kind of got the starting of neurology began with the description of this very focal aphasia type, which was associated with a specific lesion in the brain. So this is a patient that has a specific problem of speaking, but has a very intact comprehension and reading. So,
tell me, why is it that you're moving actually? All your children are grown, right? How many children do you have? What number is this? Right? Right. Now let's count it out.
1, 2, 3, 4.
Nice, nice. Well, since you did 4 so well, let's go for broke. Let's go up to 20.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, total, 1, total.
Okay.
Okay, so that's an impressive video because you see the patient has a very difficult speech, cannot say anything except this utterance, tono, tono, tono. Then when he's in an automatic mode, like counting, he can count for a little while. But then as soon as he has to think about what he's going to say more specifically, or the counting becomes at a higher number, then he returns into this. And his comprehension is fairly normal. So from this kind of data, patients with very specific neurological deficits, for many years, neurologists believed that different modules in the brain were basically dedicated to specific function. And I think neurophysiologists in the 1950s and in the 1960s and 70s followed through by identifying neurons that were specialized for different functions. So for instance, that there were description of face-specific neurons or movement-specific neurons and so forth. I think over the last 20, 30 years, 40 years, we've learned that, of course, neurons are organized in networks through anatomical connection, but still we have this notion of neuronal doctrine where there is what is important is really the properties of the local module. And this is a big debate right now in neurophysiology, is whether the neuronal doctrine is still the correct way to think about neuronal properties. I think in the last 20 years, there has been a resurgence of this idea of connectivity and distributed functions. The idea is that the properties of an area are not really depending from the properties of the neuron within that area, but they're depending on the input and the outputs. So there is no visual area, there are no face-specific neurons, but it's actually the way these neurons are connected with other parts of the brain that give rise to this functional specialization that we see when we go and record or activate different parts of the brain. And of course, this view, this more distributed connection view, leads to some prediction. And the predictions are that when you have a lesion in the brain, now the effects of that lesion will propagate through the network. And accordingly, the behavioral deficits will not be so specific, but they should be correlated because every node is going to participate in multiple functions, and therefore you're going to have a specific structure of behavioral correlation across deficits, which reflect the specific pattern of behavioral correlation across areas. Okay, and so with this framework in mind, we're going to go and start to do some experiment where the two hypotheses is, are we going to see very specific are we going to see very specific patterns of deficits, or are we going to see pattern of deficit? And if you can please close the microphones because it's coming through. Okay. So the experiment, the basic experiment that we have performed many times is the look at patients that come in with a stroke and analyze their behavior as extensive as we can, and then measure their structural damage, both in terms of lesion location and volume, their structural disconnection in terms of white matter connectivity, and their functional disconnection using the technique of functional MRI, specific the technique of resting state fMRI that allow us to study the temporal correlation between areas. So in the first experiment, we tested our patients. This is a sample of about 130 subjects with an extensive neuropsychological battery over 7 domains of function. And we have over 44 scores in which and these scores were selected to dissociate many of the neuropsychological syndromes that have been described in neurology. And so the first question is, what is the correlation across subjects and across scores? And what we found that across many subjects, we found a very strong correlation among the behavioral deficits. So this is a matrix of correlation where the color scale is the intensity of the correlation among scores and among subjects. And you see here, for instance, that if we go back to our patient with aphasia, these are all our language tasks. And you know that from neurology, you should dissociate different kind of specific aphasia syndrome. But what we see a very strong pattern of correlation across subjects. signifying that if you have problem with speaking, you will also have problem with comprehending and reading. And this is an example of some of the correlation that we see, for instance, between, say, speaking scores and comprehension scores. And you see that the patient with left hemisphere lesion has very strong correlation across the scores. Now, this is within a domain. We also have correlation across domains. And these squares here are defining principal component that were identified by studying the covariance across deficits. And out of all this work came this structure of correlation across deficits, in which we find that there is one domain, one principal component that includes language, verbal memory, and spatial memory that accounts for about 25% of the variance across subjects. There is another component that accounts for about 25% of the variance that includes deficits of attention, left motor function, spatial working memory, and sensory performance, as well as general arousal. And then there is a third component that includes mostly attention deficits of the right visual space and problem with the right side of the body. So hundreds of neurological syndromes that have been described in neurology can be boiled down at the population level with 3 scores that describe the common variability across subjects, which I think is important because this is one of the biomarkers that I think we should be carrying along in potentially measuring behavior in a computational model. Now, the structure of these deficits is also very interesting because if we do a graph of these deficits, we see that we have 2 main components. We have a motor attention component related to the exploration of space and the sensory motor interaction, and a more cognitive memory language component that is related more to the internal language verbal memory processes. And spatial working memory appears to be a hub of interaction between these domains. Now, this structure also explains recovery. So we have data at 2 weeks, we have data at 3 months, we have data at 12 months. And this structural behavioral impairment is very, very constant and allow us to basically track this patient over time very specifically. So I would say that if one has to track behavior and look at behavioral intervention, these are the kind of phenotypes that should be looked at. Now, we were interested in asking, are these behavioral phenotypes localized, explained by the location of the lesions in the brain, or maybe are explained by other kinds of features, okay? So we use machine learning models, different kinds. I'm just showing here data from a ridge regression, in which we model the behavioral results using the lesion information, both the lesion location and the lesion volume. And the story that came out of this analysis, I'm just summarizing a lot of information, is that yes, there are some domains of function in which the lesion location appears to be highly specific, accounting for almost 60% of the variability across subjects. In this case, for instance, for left motor deficits, lesion of the white matter in the right hemisphere appears to be highly predictive. On the other hand, there are other domains like spatial memory in which lesions in the brain do not explain any variability across subjects. So here we have a distinction between sensory motor deficits that are counted by lesion and cognitive deficits that are not accounted by lesions. We have replicated this data recently. When I came to Padova, we redid another experiment to replicate these behavioral results. I don't have the time to explain this, but using a much simpler scale, rather than taking 2.5 hours, it takes only 20 minutes. We were able to replicate the same 3 components, explaining about the same amount of variance. And so we are confident that this component at the population level are very robust behavioral phenotypes. All right, the second bit of information that I'd like you to remember is going back to that gestalt of stroke that I gave you at the beginning. The stroke is a cortical problem. When we collapse all this data on a single map across many, many subjects, we see that the hotspots of damage are not in the cortex, as you might expect, but actually deep in the white matter and in the basal ganglia. So this is the distribution of lesions, and you see that 63% of the strokes are actually deep, while only 10 to 15% of the stroke are cortical, purely cortical lesion affecting the cortical computation. Most of the damage is actually in the subcortical-cortical interaction or in the communication between regions. These results has been replicated in the Padova project, where basically we have almost in a separate, almost 250 subjects, we have exactly the same combination of lesion with 64%, 62% subcortical and only 14% cortical lesion. Now, we can study the structural disconnection caused by this lesion. We'll come back to this problem later. But what you can appreciate here is that a lesion, for instance, this lesion in the left temporal lobe, has a very widespread effect on the cortical connectivity, the structural connectivity of that particular location. So we see, for instance, for this lesion that is very focal, alteration both anteriorly in the brain, as well as across the corpus callosum on the contralateral side. You can also see that the amount of white matter damage is much stronger for subcortical lesion that are disconnecting many parts of the white matter as compared to cortical lesion that cause more specific deficits. Now, this pattern of structural disconnection, and this is the second point, are also relatively low dimensional. If I take more than 1,000 lesions, this is not my work, but it's work by Michel Thiebaud de Schotten, I can explain the spatial distribution of this connection across almost 1,000 lesions with less than 30 components, okay? So there is a low dimensionality in the pattern of structural disconnection in lesions, which also is good news because could potentially lead to cluster patients in very homogeneous groups that then could be treated with a relatively few numbers of treatments depending on their pattern of structural disconnection. Okay, so the first summary that I'd like you to focus on is that although we have been trained as neurologists and neuroscientists to think about a lot of specificity in lesion behavior relationship, the real world is like this iceberg. A lot of it is under the surface and is very common across many subjects. And these phenotypes are very important for population level study. The second is that strokes damage subcortical white matter connection with the low dimensional topology. And finally, and this is kind of what derived from number two, is that hence a very important mechanism for brain behavioral relationship must be the problem with functional communication at the cortical level or cortical subcortical level, which must be a major pathogenetic mechanism in stroke. And so next we're going to study what are these functional connectivity temporal communication problem that we see in this patient. Now, this is work of a PhD thesis by a talented MD PhD student at Washington University. He's a psychiatrist now. I had many MD PhD students and all of them went to psychiatry. Now, psychiatry is the new frontier, so maybe it's not surprising, but I've not been able to make any neurologists out of my lab. So what we did here, we used resting state functional connectivity. Now, this map is illustrating the temporal correlation between one area in the brain and the rest of the brain. When the color is hot, orange or yellow, there is strong temporal correlation. When the color is cool, that means there is low temporal correlation. And what you can see here, you see that, for instance, the motor cortex, which is the area that's been highlighted here, has a very dynamic relation to brain areas. Okay, so it's not a modular relationship, but it's very dynamic. And these are the signals that we're measuring. This is the BOLD signal, the blood oxygenation level dependent signal, which is a very slow signal in the range of 0.1 hertz. So very far from some of the fast neuronal dynamics. But I'd like you to remind you that a lot of the neuronal activity that we see recording from local field potential is actually low frequency. And so, in fact, the majority of the activity in the brain is low frequency. And this BOLD signal is a good proxy for that low frequency activity that we see at the neuronal level. Now, by studying the temporal correlation between areas, we can build matrices of correlation like this that identify communities And these communities, when we project them over to the brain, they represent specific functional system. And then, of course, we can have graph representation like this one, in which now we can look at the interaction between areas and the distance in correlation terms between different network. So for instance, you see here a couple of interesting things. You see that the visual network, which is this one, appears to be relatively peripheral in the system of the brain. The same is the motor network, while other network in the center here, which are cognitive network, are much more central. They're much more interacting with each other. Okay, so this is something that I would like you to keep in mind as we're going to look at the next result. So this is the normal functional organization. Okay, so now the question that we ask is, okay, now we had the ridge regression on the lesion. Let's do a ridge regression on the functional connectivity. We have data in each patient, and so we can estimate based on the connectivity matrices, we can estimate behavior and see which of the two kinds of feature explain behavior better. And so we can build different kinds of model. This slide is just to show you the richness of the results. So this is a scatter plot of predicted behavioral scores versus actual behavioral score estimated based on the functional connectivity. Here we're accounting for about 30% of the variability. These are the weights of the ridge regression that shows you the top weights that are accounting for this variability. And you see here there are two patterns. You see a pattern of interhemispheric loss, decrease of interhemispheric interaction, and increase of correlation between areas that are not supposed to be correlated. These are the two main patterns that we see in stroke. We can organize this connection by the type of connectivity, interhemispheric or intrahemispheric. We can organize them by network, okay, functional networks, or we can project them on the surface and see what cortical parcel are actually explaining our behavioral variability the most. And you see that this yellow parcel in this particular model are the one that are accounting for the most variability. Now, going back to the question of prediction, here's what we found. And I think the results are very interesting. If we look at sensory and motor domain, visual deficits, primary visual deficits, and motor deficits, we found what we saw before, that the lesion is much more predictive than the functional connectivity. The lesion explained 40 to 50% of the variability. The functional connectivity is not very predictive. In contrast, when we go and look at cognitive domains, like verbal memory or visual memory, in which the lesion is not doing very well, now the functional connectivity predicts a lot, okay? Now, there are some domains, and that's also very interesting, like language in which both lesion and functional connections are predicted. So language is kind of special. Language seems to be, in a way, has very specific areas where the damage of these regions are affecting behavior particularly, but other domains like visual and verbal and attention, which are much more distributed in the brain, now you need to look at the pattern of connection in order to understand what's going on, okay? So the take-home message is that sensory motor deficit, you look at lesion, cognitive deficit, you look at functional connectivity. And these are some of the map of the ridge regression for the lesions, and I don't have the time to comment on the topography of this map. And these are some of the topology of the connectivity that are explaining behavior. And again, what I like to underline here is the low dimensionality of the kinds of connectivity abnormalities that we see in functional connectivity. Again, independently of the domain of function, you always see the same pattern. You see a loss of interhemispheric connectivity, and you see abnormal connectivity in intrahemispherically. Okay, now these two patterns give rise at the graph level to a loss of modularity. The modularity of this network is decreasing because there is more integration within the hemispheres. Okay, now that's the good news. So the patterns are always the same, irrespective of behavior. The bad news, of course, that you see how widespread are these abnormality for lesion that can be also very small. In fact, on average, any stroke lesion causes between 25 to 45% of connectivity abnormalities across the brain. That is, 20 to 45% of your connection are out of sync once you have a stroke, even if the stroke is very small, Okay, so the good news is that the pattern is the same. The bad news is that the topology of the abnormality is very distributed, which is really bad news for any kind of neuromodulation attempt. Here's another way to look at what these results are showing. These are the different domains, and each one of these circles is weighting the predictive connection across the different networks in the brain. And I'm going to highlight a couple of different patterns. This pattern that appears to be relatively constrained to the specific system. So motor, for instance, is accounted mostly by motor connectivity problem and much less from cognitive. The same for visual, and to some extent the same for language. In contrast, look at visual memory, attention, and verbal memory, how the weights are fairly distributed across the brain, okay? Now, why this happens? We think that this happens because of the normal functional organization. I told you before that the visual and the motor system are peripherally in the brain network, and also the visual and the motor system are strongly connected with the periphery. The visual system through strong white matter connection to the retina, the motor system to strong white matter connection to the spinal cord. In contrast, association connection are presumably or predominantly maybe more redundant. There is more redundancy in the center of the network, and this might explain why these effects are more distributed and less depending on lesion location, okay? Okay, so to summarize the second part, I try to show you the stroke lesion, irrespective of their location, cause widespread alteration of cortical functional connectivity that are relatively stereotypical, including these two patterns that I see. However, the topology of this alteration is widespread and involves multiple networks, okay? So these are the two main take-home messages. So attempts to neurostimulation must take into account this complex functional anatomy, and therefore, of course, most of the neurostimulation attempts to date have been done by single-site stimulation. I think the future must go to multi-site stimulation with appropriate computational modeling, and that's kind of where we're going with our research program. All right, in the third part, of course, I show you the effect of the lesion, and I show you the effect on the functional connectivity. But you might ask, okay, well, what is the relationship between the structural connectivity and the functional connectivity? I'm not going to spend a lot of time. This is a big paper. I'm just going to show you the highlights. But the highlights basically is that, of course, functional connectivity and structural connectivity are strongly related. This is work by a very good postdoc, Joseph Griffiths, who's now advanced to faculty position. And basically what Joseph did, he built for each one of these patients what we call a structural connectome. That is a map of the connectivity between all of his regions, all the regions of the brain in particular subjects, and then estimating the connection that are damaged in each subject, okay? Like I showed you before earlier, okay? So these are structural disconnection map for each subject. And then we ask the question of how common, similarly to what we asked before, how common, how frequent are the structural disconnection in cortex as compared to the lesion. And you see, this is the distribution of the lesion frequency map. You see that the lesions are occurring in multiple locations. They're not clustered in any particular cortical location. In contrast, they're clustered in the basal ganglia. But you see here, there is much more clustering at the cortical level in terms of the structural connection. Again, these are all the interhemispheric structural connection, they're damaged. And then there is also a lot of clustering in terms of subcortical to cortical connection. A lot of the thalamocortical and striatocortical connection are consistently affected by stroke. At this point, we can build statistical model, for instance, a partial least square correlation that relates in each subject and across subjects the pattern of functional disconnection with the pattern of structural disconnection, looking at the covariance between these two topological patterns. And this is kind of, I have to spend more time. I'm just going to give you the take-home message. But the take-home message is this. You see here in blue, the latent variable of this partial least square correlation. And the latent variable, the first latent variable, is accounting for 40% of the covariance. In other words, there is a particular pattern of covariance that is explaining 40% of the variability across subjects. And then there is a second pattern that is explaining about 18% of the covariance. So again, this is good news for neurostimulation because it says that across hundreds of lesions, despite their relatively heterogeneity in terms of location, the low dimensionality of the structural disconnection and the low dimensionality of the functional disconnection give rise to correlated pattern of structural functional abnormalities. And these are basically the main pattern. This is the top component, the first latent component. And this is basically showing that the interhemispheric disconnection that we see at the population level is causing two kinds of correlated functional disconnection pattern. It's causing the interhemispheric disconnection that I described, and it's causing also a correlated intrahemispheric integration that I also described. So these results show basically that this pattern, the loss of coordination between the two hemispheres and the abnormal integration within the hemisphere are related signals. They're related to the way the connections are set up, to the effects of the stroke. And the main effect of the stroke is the disruption, the structural disruption of the callosal connectivity. Okay. So to summarize, what I show you so far is to show you basically this interesting multi-relation between a lesion, okay, is behavioral low-dimensional result, as well as low-dimensional pattern of structural and functional disconnection, okay? And so this is, again, what we see from all this work on the static properties of this network and this lesion and the behavior. In the last 10 minutes, if I have time, the chair, I don't know if I'm in time or I'm running out of time. I think I have about 40 minutes here on my 30 minutes on my watch. Mufti?
I think it's okay. Yeah.
Okay.
Yeah, please.
All right. In the last part, then I would like to focus on some of the dynamic properties of these alterations. Okay. This is work by a great postdoc in Padova, Chiara Favaretto, who is basically asking two questions. Do lesions affect brain dynamics? Okay. And do lesions cause new pattern of dynamic interaction, or do lesions alter patterns that are already present to some extent, or just changing the landscape of dynamic interaction in the brain, affecting, maybe biasing some pattern more than others? And by using dynamics, do we improve the prediction of behavioral deficits? Okay, so these are the two questions of this project. So the first question is how to extract dynamic communities out of these kind of signals. Again, I remind you, this is the time course of bold activity between two regions in the brain, the region on the left and the region on the right. In the case of stroke, the correlation between these two regions is altered, okay? Now, the pipeline that she developed is one of the simplest possible way to extract patterns of dynamic functional connectivity. Basically, what she does for every frame in the Bolt signal is extracting, for every 30 seconds of the Bolt signal, she's extracting a correlation matrix, okay? So we have a series of correlation matrix across all the brain region, is extracted first eigenvector for each matrix, and then she's then reconstructing the matrix based on that eigenvector. At this point, we have a single vector that is explaining that point in connectivity for that particular subjects. We're putting all these dynamic pattern, all these windows of connectivity concatenated together, okay, across controls, across patient at 2 weeks, across patient at 3 months, and across patient at 1 year. This is a longitudinal example in which we have the same patient study at 3 time points. And then using very simple k-means at different level, we optimize based on different optimization method. We found, we did the analysis at different level, but I'm going to describe 5 clusters, okay? 5 what we call dynamic states are representing basically patterns of correlation between areas that are occurring consistently in the analysis across subjects and across different time points. Now, from these dynamic patterns, we can extract some dynamic measure. For instance, the frequency of occurrence of a particular pattern, its average lifespan, and the transition probability of different patterns. These measures are correlated among them, and so we can extract some summary measures of dynamic alterations or dynamic descriptions, and then we can use this dynamic measure using, similarly to what we've done before, with the ridge regression to basically study the relationship between dynamics and lesion, dynamics and connectivity, dynamics and behavior, okay? So it's the same kind of statistical framework, but rather than using static measures, now we're using dynamic measures, okay? Now, again, this is another big paper, so I don't have the time to, but this is basically the correlation structure at the network level that we see across these 5 states. Now, for those of you that are fun on networks, there are interesting fun bits in here, but the point that I like to emphasize is that these 5 dynamic states, okay, that representing 5 different kinds of correlation across networks, vary in some of the properties that we see in stroke patients. In other words, DFS1 and DFS3, this one, have the strongest interhemispheric interaction of all the pattern. In contrast, for instance, DFS1 is the one that showed the more normal segregation pattern in the normal brain, okay? These other patterns are relatively more integrated. These other states are relatively more integrated. The modularity, which is one of the properties that drops in stroke patient, is best captured by DFS1 and DFS3 and much less by DFS2 and DFS5. So the point that I'm trying to make here is that the normal dynamic properties resemble, okay, capture some of the property that we see lesion that we see affected in our stroke population, okay? So there seems to be a relationship here, which I think is very interesting. Okay, so then at this point, we can ask the question, what happens in control patients? What is the distribution of the states in control patients? And what is the distribution of the states in our stroke patients, okay? And what you see in controls, all the patterns are relatively equally represented except 5. In contrast, in stroke, we have an overrepresentation of 2 and 4. They are the most integrated states in controls, okay? So it looks like that the brain in stroke patient is biased towards more integrated states and less segregated states, dynamically speaking. Now, the interesting results is that at 3 months and at 1 year, the distribution of states in this patient normalizes, consistent with the behavioral recovery that we see in the patient themselves, okay? The second point, and this is the last data point that I'm going to show you, is that we find interesting subcortical cortical interaction. So there are certain cortical patterns, okay, certain cortical states that correspond to specific subcortical states. And this is true for all the patterns, okay? And we were interested in understanding whether the subcortical states were actually highly heterogeneous or were actually relatively homogeneous. And what we discovered is that the subcortical pattern divide in 2 interesting classes that are anatomically motivated. There is one cluster that we might call a neocortical cluster that defines striatal cortical loops. And then there is another cluster that is defining more limbic nuclei of the cortex, like the hippocampus and the amygdala. These 2 patterns of subcortical correlation, they tend to be of different sign, of opposite sign. When one is on, the other is off, and vice versa, okay? There seems to be a push-pull in the subcortical nuclei. And when we look at dynamically to this push-pull in the subcortical nuclei, you see here points of switches between the subcortical clusters. You see correspondingly, there are switches in the cortical dynamic states. You see how these networks are changing, and they're changing their state exactly when the subcortical nuclei are changing. So we're now in the process of running some directionality analysis to see whether in fact is the subcortical nuclei, they're actually directing the potential switches in cortical states. Now, when we look at what is explaining the dynamic changes in our patients using the same ridge regression model, we find that the patients that have the most dynamic alteration are the patients with subcortical lesion, as you can see here in this map with the blue color indicating the lesions that are affecting the most the dynamics. And also, in terms of the structural disconnection, are the striatal cortical disconnections that explain the most of abnormalities in dynamic properties, okay? So this is actual causal evidence that alteration of subcortical to cortical communication is actually causing significant problem in cortical dynamics. And finally, this seems to have a greater explanatory power than the static connectivity by itself. So this is an analysis of language in which we can predict chronic language scores based on the dynamics and based on the combination of the static and the dynamics, but not the static. And the same for verbal working memory, where we have very strong prediction based on the acute dynamics, but not the static dynamics. So we think this is a very exciting result because it suggests that studying the cortical dynamics explains some of the variants in our behavioral deficits, and it might have also predictive abilities for the future, for predicting the final outcome of this patient. So to end and summarize, what I show you is that focal lesions affect brain dynamics with a bias towards states of greater integration. Cortical states are flexibly synchronized with subcortical nuclei, representing either motivation memory, the limbic nuclei, or action signal, the striatal system. Basal ganglia cortical connection causally change cortical dynamics, and brain dynamics add to the prediction of behavior. So, to end this lecture, I think what I'll try to show you here is that the relationship between a lesion in the brain, the underlying structural and functional interaction in the system, and the behavior is a very complicated, multidimensional, multi-scale mapping, okay? As I said, there is both low dimensionality, which is good news, but also high topology and high variability in terms of location. So this is a very difficult problem to model, okay? But it is possible, and we are actually looking at this kind of whole brain modelings, in which basically you can use structural connectome to generate neurodynamic models in the healthy brain, and then make lesion in the structural connection to look at whether you can replicate some of the both static and dynamic abnormalities that we see in our patients. And then, of course, if that works, then to go to stimulate this model to potentially restore some of these static and dynamic properties. I'm going to close by thanking my collaborators, both in St. Louis and in Padova, and I thank you for your attention, and I'm sorry if I'm a couple of minutes late.
Okay, thank you very much for Professor Kobeiter. It's a very interesting talk. So we have a few minutes for questions and the discussions. Any question, please? Okay. Yeah, please.
If I may, I'm Stefano Bassanelli. Yeah, so thank you very much for the very exciting and insightful talk, Maurizio. So basically what emerges, if I correctly understand, is that subcortical structures are playing a major role, particularly striatum. So what maybe I would like you to comment on is what about modeling? So you a little bit touched the topic in the last slide, but I think most of the modeling has so far focused on cortical connectivity, cortical areas, and little that has been done, as far as I know, on modeling subcortical structures and their connections to cortical areas. So how, in perspective, I mean, do you think it will be an important effort to concentrate also on understanding how to model subcortical structures, and maybe on which one we should focus in the future?
I mean, yeah, this last result for us were very surprising because, a lot of the theory about cortical communication has emphasized, well, some theories has emphasized hubs in the cortex. So the role of, central regions in the cortex that are coordinating the communication between areas. And in our lesion analysis, we don't see any evidence that having lesion in particular brain regions, cortical regions, is actually affecting communication. There was a slide here that I went on through very quickly. And instead is the subcortical. Now, there are good subcortical parcellation, both structural and functional. And so people are beginning in our modeling with the Gustavo Decor, actually beginning to model subcortical nuclei and subcortical interactions. The problem is that the spatial resolution in the subcortical nuclei is not as good. And so as you saw, my subcortical nuclei are kind of very not specific. So I think we need to first refine the subcortical atlases, and there's been some recent work on that, and then be able to model the subcortical cortical interaction. But I think that's going to be a key problem for understanding both normal physiology as well as the patients. Yeah.
Thank you.
Okay, thank you. Any more questions? Okay, maybe I have one more general question. Yeah, thanks again for the Professor Kopita. It's a very interesting talk. But I think for the clinical issue, maybe also should be consider about individual difference. I mean, your proposed this model is a statistical group. You use some group data. Yeah. What do you think about the individual difference for the clinical issue?
Well, it depends on what we're trying to do. I mean, if we want to model individual differences in cognition or behavior, of course, then you have to look at individual differences. Now, as a neurologist, I started with this idea 10 years ago that every patient was different, and every patient was to have and instead, by looking at these groups, I can see that there is commonalities, and the commonalities are explaining for 60 to 70% of the behavior. So if I can fix 60% of their deficit, I would be very happy. So I think I would, at this point, we're focusing on what is common. And so we're actually concentrating on these common patterns to see whether we can actually fix those. And then, we're going to worry about the individual differences later, I guess. So.
Yeah. Okay, thank you. Any more questions?
Mufti, you have a question? Yeah.
Yeah. Well, I just actually wanted to request you to shed some lights and some of your experience in terms of the analysis techniques, because, well, given that these days a lot of machine learning and deep learning based techniques have actually been employed in understanding certain patterns, even in single brain imaging data. So not with let's say a lot of them, but with some of these studies, they have shown quite promising results. So in your opinion, where should the efforts be in terms of the development of different analytical methods or analysis methods for analyzing and deriving some meaning or meaningful conclusions for these kind of images that are being presented here?
I mean, we use mostly, we use linear methods because we were interested in projecting back some of the weights, right? I mean, to have a representation. I mean, if I do a deep learning network, then I think the features are going to be much more obscure. So I was interested in plotting back into the brain, the lesion location and the functional connectivity and all of that. Now, in terms of the behavior with Marco Zorzi, he has done an analysis comparing linear, nonlinear, and support vector technique in deep learning. And in terms of the behavioral prediction, I think the results were that there was not much difference, that linear technique were doing quite well. So I think maybe for group analysis, we don't need to go through, I mean, if we're going to start predicting single subject, that maybe we need more power, but then of course you got the problem that some of the features are not as easily plottable onto the brain. And I think it's a big limitation to me, because I want to understand mechanisms, and I think predicting just behavior is not good enough for predicting just, you know.
Yeah, thank you very much. Yeah.
Okay. Any more? Yeah, maybe it's just time. Yeah. Thank you very much again for Professor Corbetta. It's a really excellent talk. Yeah.
Okay. Well, thank you, and we'll wait you in Padova next year, hopefully.
Yeah. Really hope next year we can. Yeah.
We're going to show you some of the nice features.
Yeah.
Okay. Bye.
Bye-bye.
Yeah,
thank you very much. Yeah. Maybe we close this session to the next. Yeah. Thank you very much.
Okay.
Okay, so should I take over, Mufti?
Yes, please. Yeah, please.
Okay, so it is time for me to introduce the next keynote speaker. So I've seen he has been joining. So Stefano Panzeri, can you hear me, Stefano?
Hi, Stefano, I can hear you, and thanks for the invitation to the conference, and thanks everyone for attending.
Great. So I see still the slides from Professor Corbetta on the background, so maybe, okay, thank you. Good, so, well, of course, it's for me a great pleasure to have here Stefano with us. He's a great scientist and also a friend, yeah, so I will shortly introduce him and then give the floor to him. Yeah. So basically, I go through his biography quickly. So he's a physicist. He's actually, as a background, is a theoretical physicist, and now he's actually recently moved to Germany, and now he's director at the Center for Molecular Neurobiology, Hamburg. The Department of Excellence for Neuroinformation Processing of the University Medical Center, Hamburg-Eppendorf. So, as I said, he received the degree in physics in Turin, and then he moved to Trieste to the International School of Advanced Studies. And then, let's say, skipping several steps in his career, he got appointed full professor at the University of Manchester and then Glasgow. And then he was back in Italy for a period as a senior researcher at the Italian Institute of Technology. He was also, of course, visiting scientist at the Max Planck Institute for Biological Cybernetics and at Harvard Medical School. So at the Max Planck, he has been working, for example, with Nikos Logothetis, doing fantastic work there. And then he was also coordinator at the Center of Neuroscience and Cognitive Systems of the Italian Institute of Technology. He also served as deputy chair of the UK Medical Research Council panel for fellowships in bioinformatics and neuroinformatics. And yeah, and that's essentially just some highlights about the career of Stefano. But I think as a research interests and topics, I think it is important for this conference to highlight that he is one of the, I think, really gave fundamental contributions, and still working on that, on the theory and theoretical aspects of how neurons basically generate signals that we record in the brain, and how we can interpret them in terms of extracting useful information from these signals, which is, of course, a great and important question for neuroscience, computational neuroscience, and understanding of brain function. So, and is also developing new computational let's say, tools, models of neural function and tools to extract information from brain signals. So basically, this was my brief introduction. So Stefano, I give you, it's a great honor for me to give you the floor for this talk. Please.
Thank you. I think the talk was pre-recorded as required by the conference organizer. Just one small note, that since we are all very fatigued with, long talks and so on, I thought of doing like a shorter talk of about half an hour, and then maybe leave a little more space for the discussions. So I hope it works. Okay, thank you.
Yes, well, I'm going to play the talk now. Yeah.
Good morning, everyone. My name is Panzeri from the University of Hamburg and from the Italian Institute of Technology. And I would like to thank the organizer for inviting me, to this wonderful conference. And today I'd like to talk about our work on inferring neural circuit interactions and neuromodulation from recordings of local field potential and electroencephalograms. And this is work that we did with our collaborators. In particular, I'm grateful to the work of the people in my lab who contributed to this, especially Pablo Martinez and Shariar Noé. And also I'm grateful to the collaborating labs that provided all the experimental input, experimental data to our theoretical work. Nikos Logothetis, Alessandro Gozzi, Tobias Donner in particular, he gave data that will be used in this talk. And also Gaute Hannibal collaborated a lot on the theoretical collaborations. And so this talk is about developing computational methods to better interpret and understand electrical recording of mass neural activity, such as, for example, local field potential or electroencephalograms. And these mass signals are computed either intracranially in the case of the LSP or extracranially in the case of the EEG by putting an electrode. And for obvious reasons, these mass signals can capture all components of neural activity. They are sufficiently spatially organized to sum up and produce a weak electrical potential at the level of the electrode or at the scalp. And also they are sufficiently temporally coherent. And so they capture a lot of stuff. But to first approximation, it is believed that their major contribution is the superposition of dendrosomatic dipole fields generated in apical dendrite of pyramidal neurons, which is, as shown in this diagram, those apical dendrites are organized in a kind of aligned way, so they have a better chance than other contributions to survive the mass averaging. And those signals are widely used, and for good reasons. And one reason is that they capture multiple contributions to neural activity, including saturation, integrative, synaptic dynamics, which is out of reach if you just measure the spiking activity of small populations. And also those signals are really wonderful for detecting oscillatory activity. And so all these studies of synchronization, oscillations across areas and so on, those are based mostly on field potential or electroencephalograms because they can capture really well oscillations. And also these signals correlate with another widely used measure of neural activity in humans, non-invasive. That is the functional magnetic resonance imaging signal. It is well known from the studies of Logothetis and colleagues that field potential, for example, especially certain bands like gamma band, correlate much more to the ball than spiking activity. So studying these signals also is useful because it allows a link with these other major kind of studies. And so, the strength of this signal, which is they can capture a lot of interesting stuff, is also their weakness, because given that they are ambiguous, they don't have a cellular resolution, and they capture a lot of stuff, so they need to be decomposed in terms of the original constituents before they can be interpreted. And in particular, they are broadband, so they capture a lot of stuff. So as we'll show later, if you put an electrode, you get a lot of oscillation over a wide range. And it is difficult to separate this broad spectrum into components, each reflecting a different component, a different aspect of neural circuit activity. This frequency band separation is to a large extent arbitrary, and there is no golden rule to be able to separate the signal into different components just looking at the spectrum. And they are difficult because they capture a lot of different stuff. They're difficult to interpret directly in terms of neural phenomena. If you have, for example, an up and down or an increase on LFP power or a change in phase and amplitude of the signal, how do you interpret them in terms of, say, activity of excitatory neurons, activity of inhibitory neurons, and so on? That's very difficult to do. And our computational work is aimed at helping experimentalists with tools that are potentially, we hope, are potentially useful to better interpret these signals and identify the neural components that originate them. In particular, our work proposes to first individuate, in quote, independent or at least largely different neural processes that contribute to field potential or electroencephalograms. And especially if you are interested in sensory function, try to determine what are the main information channels, the main information avenues that are reflected in field potentials, and try to understand what is the function of each component of the field potential in terms of computation. And once we have individuated the main independent principal phenomena with some computational analysis, we would like to use neural network models to understand the mechanism, the actual nuts and bolts mechanism generating the cell phenomena. For example, where does a band come from and what information it conveys and so on, why, what are the neural mechanisms. And once we have this understanding, we can use the neural network models in a more quantitative way to invert the recordings and actually estimate the network parameters, the neural network details. For example, excitatory inhibitory firing population that gave rise to the observation. If you do that, I think we can use this tool to kind of reverse engineer neural computation based on the measure of the signals. And I will provide one principal study to explain our logic, but I mean, we did also other studies. I will explain why this study is good enough, I think, to give an overview. And the reason, I mean, this is a study where my colleague Nikos Logothetis and others, his collaborators in Tübingen, recorded the local field potential with arrays of electrodes on the primary visual cortex of macaques light anesthetized with OPAs. So here eye movements were blocked, so the input visual stimulus coming to the visual cortex was very well known. And as visual stimuli, we used the movie stimuli, Hollywood movies. And the reason is that we wanted to really try to decompose all the possible neural information channel that you could capture with the field potential. And we thought that exposing the system to a very complex stimulus with a lot of static image properties, contrast, color, and so on, and also dynamic properties, like the changes that happens in the movie across different frames. So if you had all of these, there would be a better chance to kind of activate each specialized information channel that is captured by the field potential in a different way, because those things vary from scene to scene of the movie, I think, not completely independently, but in a large independent way. So there was a better way, I mean, with the stimuli, with respect, for example, with I don't know, gratings or very simplified stimuli, to identify the different neural phenomena that you can get in a field potential. And so the first analysis we did was the traditional analysis, where you just take the whole spectrum and you compute the oscillation power with Fourier analysis. And if you do that, you get something like this, which is the very typical field potential cortical recording. You have wide band fluctuation from a fraction of a hertz to more than 100 hertz, so several octaves. And there is no clear peak in the field potentials. So it's not so easy just looking at this stuff to tell, well, I have 1 band, 2 bands, 3 bands, where is the stuff, what is the most important part of the spectrum. So the question we have to understand, starting from the signal, is how to partition the signal in different bands in an objective way. And also, once you have bands, how to identify the neural origin of each frequency band and also identify its function. And to do that, the first step was to use a metric, which we felt was more sensitive and more suitable for those issues. The metric was mutual information from the theory of Shannon. So we computed mutual information that the power of each frequency carries about which scene is being shown at the given moment on the retina. And here you see an illustration of this computation. And what is important to understand here is that the way we designed this computation was general, very general. And so we were able to quantify and capture all, the information about all possible stimulus features in the movie, including single image frame properties and dynamics across frames. So this way we could really capture all information about essentially all possible visual attributes that you had in the movies. And if we did that, we found, rather than a spectrogram, an informationgram, as we call it, which is something that you see on the right here. And this informationgram tells you how much information you have in each frequency band about all the possible visual stimulus in the movie on average across sessions. And if you compare the spectrum with the informationgram, you see that the information theoretical analysis reveals a sharper distinction between different frequency bands, which you cannot gain just measuring the power. In particular, it seems to be clear from this that you have two different informative power signal region, which is the low frequency band highlighted in green here, which comprises the traditional delta and theta and maybe a bit of alpha band, and also the gamma band, this high frequency band between 50 and 100 Hertz approximately, which carry higher amount of information about the movie. And in between, you have this kind of intermediate frequency information, which is roughly the beta band in terms of classical frequency band names that does not carry much information. So at least with this, you identify bands. But then you could ask, is this like, are the low frequency and the frequency bands really different neural phenomena? Is it more of the same stuff and so on? And there are several ways to do it. One way that we did to address this issue was to compute the so-called signal and noise correlation between the powers of all pairs of frequency bands. What we found was that you had some signal and some noise correlation within the low frequency band. You had some signal correlation within the gamma band. So those bands legitimately, the low frequency band and the frequency bands, are bands that carry in a way similar stimulus features. But if you look at the signal and noise correlation between the low frequency and the high frequency bands, you would find both zero signal correlation and zero noise correlation. So this low frequency band, this high frequency band, did not share any similarity in covariations, not due to the stimulus with this noise correlation, and did not share any similarity in stimulus tuning. So they were essentially completely orthogonal, completely independent information channels. And because of that, we hypothesized that they reflect different neural pathways, neural interactions. And to study this a little bit better, we coupled this information theoretic analysis with another computational analysis. This computational analysis was the biophysical modeling of those field potentials. And to do that, we started, since we recorded essentially local population in V1, in primary visual cortex, modeling, the most simple form of interaction that you have within a local circuit, which is the recurrent interaction between excitatory and inhibitory neurons. You have that in every cortical region. You have that in visual cortex. So we had a network that had the excitatory and inhibitory neurons, and also a network that had the thalamic input that could carry sensory information, and also other cortical inputs. And this one was done with point-like neurons, integrated fire neurons. And the big advantage of that you can really understand very well, even solve analytically in some cases, the dynamics of those circuits. So you can really understand what those circuits do. But at the same time, those models are simple enough to be solved analytically or studied numerically well. But at the same time, they can generate a very rich repertoire of dynamics, which includes, for example, weak synchronization and so on. So dynamics that you see very well in visual cortex. And as you will see in this data, those simple models can explain more than 90% of the variance of the data. So they work very well. But those models have the problem that they cannot generate any field potential or electroencephalogram because they are based on point-like neurons. And therefore, field potential and the electroencephalograms are generated by special gradients in the current. If you have point-like neuron, you cannot have a special gradient. And so in order to generate the field potential from this network, we needed somehow to match our point-like networks to network of realistically spatially extended neurons. So we thought of a kind of hybrid approach to do that, which was simple enough to be studied well. So we had the spikes generated by this integrated and fire point-light network that we studied very well. And then we projected those spikes into 3D models of neurons with various morphologies. And we let essentially those 3D models of neurons generate using Maxwell equations a realistic field potential or electroencephalogram. And then we did the statistical learning process to learn a correspondence between the spikes of those networks, the activity, the synaptic currents of this network, and the electroencephalogram. By doing that, we found the function or proxy. It could be linear or nonlinear, but works very well. That describe what would be the field generated by those point-like neurons if they were spatially extended. And from this, using various techniques, essentially we could compute and validate that this proxy works very well, gets more than 95% of the variance of the data, the simulated data, and so can be used to really generate in a very compact, very easy way a realistic field potential from those simulations. And those simulations, once you do that, work very well, and you can explain about 90% or more of the variance in real data based on those simple models. So it seems to be a reasonably accurate approximation. So using this approximation, we studied what are the different possible origin of this low frequency and high frequency information channel that we found in V1 in the field potentials. And to cut a long story short, by applying this realistic model that explain a lot of variance in the data, we came to the conclusion that these low frequency oscillations in model, they encoded the slow dynamics of the thalamic inputs. So the prediction that in data, those low frequency LFP oscillations should be entrained to slow variations, for example, in contrast or other visual features in the movie. And if you look at the real V1 data, we found exactly that. We found, shown in this little picture here on the bottom, is that the time course of variations of, I think this was luminance in the receptive field while you present the movie, led to an entrainment of the field potentials exactly in this low frequency band. So this prediction of the model was confirmed by further data analysis. Then we look at the origin of this information in the gamma high frequency channel. And we know from the theory of the neural network, in particular from the very nice work of Nicolas Brunel and Jiajie Wang, that those oscillations in the range we observed are generated by recurrent connection between inhibitory neurons and excitatory neurons. And those neurons also we know, and we simulated, as we show here, that I mean, the interaction and the strength of the gamma synchronization that they generate is a function of the external input. The stronger the external input, the more you have, the more power you have in this band, as shown in this figure here on the left. So based on this, we hypothesized that the model, the gamma band encoded static visual images. And the reason is that the static visual images, the feature modulate the firing of the neurons, and they should be reflected then into changing input to the network overall level, and therefore changing gamma power. And again, a prediction is that in this way, you have to find visual features, static visual image features that modulate the gamma power, and you find that as well, especially special feature at fine scales, they seem to modulate the gamma LFP very well. And we put all of this into a model. So we took also thalamic inputs, lateral geniculate nucleus recorded with the same movies simultaneously with the LFP data. We fed them into the model. We let the model generate activity and information. And we found that the model reproduced very well this U-shaped curve that you found in the data. So essentially, the model is able to explain very well all this stuff. And this this model explained very well the information in low frequency and high frequency oscillation, but it could not reproduce any of these high power in this intermediate beta band that had no information. And to understand why, I mean, where this comes from, and we said we made the hypothesis that given that it had a high power, but did not carry information about the stimulus, and was not generated by this recurrent interaction between excited and inhibitory neurons, we hypothesized that this could be due to changes in neuromodulation. And so to kind of prove that, we did an experiment where we injected systematically dopamine. So we manipulated dopamine, we led to an increase in dopamine under the same experimental conditions than before. And this increase in dopamine led to an increase in power only at exactly in this band that is not used to convey stimulus information. So again, the prediction of our theoretical model were confirmed experimentally. So to cut a long story short, here we took a spectrum of neural activity that was difficult to interpret. And then using computational model, we turned that into an information gram. And then further analysis of this information gram led us to identify low frequency oscillations in visual cortex as entrainment of thalamic inputs and encoding temporal movie variations. We identified the gamma power as coming from excited to inhibitor interaction within the network and encoding static image properties. We identified this gamma band reflecting neuromodulation, in particular dopaminergic neuromodulation. And as a result of this, using the computational models, we came to, in our view, the first complete breakdown of the whole of oscillation spectrum of the cortical area in terms of neural mechanism and function. So this, I think, illustrates the power of those kind of techniques when applied seriously throughout the various aspects of the data. And the success that we had in using those models to using those models to interpret the data led us to maybe try to bring this kind of process a step further. And the step further is to use those tools then to actually quantify exactly, so use them as analysis tool to quantify what are, for example, the changes in excitation and inhibition or interaction between the neurons and so on, while you record the field potential or magnetoencephalogram or an electroencephalogram. And therefore, we try to essentially go forward. We divided the work in 4 steps. The first was to study analytically and numerically, very carefully, the relationship between microcircuit neural parameters and this mass signal, field potential, EEG, and we even did the fMRI, which I don't talk about today, but we even did that. You have that in a paper published last year in eLife. And so this is essentially along the lines that we discussed. And then, based on this detailed analytical and numerical understanding, we developed a statistical learning model of how the feature of field potentials or electroencephalogram depend on neural parameters, and we use that to fit model to data estimate neural parameters. Once we have this function, this inversion function that given spectra of field potential EEG gives you an estimate of neural parameter, we try to validate them by using data where you perturb some feature of neural activity, for example, excitation and inhibition, and you see whether your model, just based on electroencephalogram or field potential, is able to predict that. And so once the model is validated, hopefully we use that to invert electroencephalogram, magnetoencephalogram, and you name it, of humans in terms of neural parameters, and help therefore to understand neural computations in the human brain, both in function and dysfunction. And I'll give you some example of this work which is in progress. So interventional test, our colleague Alessandro Gozzi, Federico Rocchi at IIT did a number of experiments where they manipulated neural activity in prefrontal cortex with chemogenetics, and they did various types of alterations. Some that would increase excitation, and like the one on the bottom, and some that would decrease excitation. And what we did, we took the spectra recorded under those conditions, we analyzed them with our methods, and then we essentially measure excitation and inhibition in the tissue, in the neural tissue, with our algorithm based only on the field potential spectra. And in all cases that we analyzed, we found that our algorithm was able to tell if the manipulation applied was increasing excitation and decreasing inhibition. So the method was validated. Then also we did with Tobias Donner, Alessandro Toso at here University of Bangor Medical School. We also did some work to try to validate those kind of data in human data. And we took magnetoencephalographic recordings from Tobias' lab. And in this, they did the pharmacological manipulation. They administered to the volunteers memantine, which is an MDAR agonist. So it's supposed to increase the ratio of excitation to inhibition in favor of excitation. And then we use our method to measure across the brain with suture reconstruction whether excitation and inhibition was changed in each area. And again, here the method was able to identify the kind of systemic manipulation that was applied. So again, the method was successfully validated. And then another thing that we did, just as an illustration, we said in this last fourth point of our research program for the next couple of years or so would be to use those models when they're validated to reverse engineer some neural computations in the human brain while they do tasks. And one simple application that we did here was to use our method to actually estimate in control patients, so patients without any pharmacological manipulation, in control people, control subjects, so subject without any pharmacological manipulation, whether the excitation and inhibition ratio would change over the cortical hierarchy from sensory to parietal, that is association, to frontal, that is decision areas. And there are various theories that suggest that excitation would increase as you go from sensory areas to higher level areas. And this is exactly what we found again in this application. So this model seems to be able to give some help reverse engineering neural computations even in the human brain, and seems to be able to give credible results that stand with popular theories about this issue. So in summary, we presented a little bit of our computational work, which I think we hope at least is maybe useful to disambiguate and interpret mass electrical recordings of neural activities, self-field potential or electroencephalograms. And we use statistical analysis to identify independent neural phenomena and their contribution to information coding and so on. And this included also help designing interventional experiment like the dopamine one. And we did network modeling on the neural phenomena, independent neural phenomena identified that was aimed at identifying the neural mechanism and neural computation and neural pathways generating each band. And with this also, we would like to push this forward to not only to propose generic qualitative explanation of the data, but to actually infer the hidden network parameters on experimental data that you cannot record just on the EEG or left directly, but then you can infer by model inversion using our models. And next steps, final steps for us is to improve our tools to estimate neural parameters. In this application, we did excitation and inhibition ratio, but we would like to estimate other things like input to the network, overall excitability, and so on and so on. And this is ongoing work. And Pablo Martinez has a paper B204 in this conference where he will illustrate and report the latest advance that we have on this respect. And I'd like to take the opportunity to thank everyone for their patience in listening to their talk, and they will be available for questions in the next session. Thank you very much.
Okay, so thank you very much, Stefano, for this video. I think it was a very nice and insightful example of how pervasive is information theory applied to neuroscience. So from the, I mean, it sketched very clearly the approach from the data to the modeling. Yeah, so very clear. Yeah. So I don't know if there are questions. Otherwise, I have definitely one, and I have a curiosity about. So, any questions from the audience?
I have a question.
Yeah, please, Maurizio. Sorry.
Stefano, very, very nice. I was wondering, I mean, what is your, I mean, the modeling is it's kind of bottom up. I mean, it's basically taking sensory signals. And so, but do you see, how do you see, or how do you foresee modeling kind of the let's not call it top down, but let's call it, I don't know, expectation, or because we know that there are during tasks this very, and also we know that the connectivity, the feedback connectivity is actually very dominant, even from a connectional perspective. So how do you see moving the model forward from modeling the sensory input to modeling the internal states and the sensory input?
I think some of the model features already include some of these. For example, there are terms that can include neuromodulations. And this example essentially that we saw, was of essentially guessing that some band in visual cortex would be driven by dopamine, even if the visual cortex doesn't have dopamine receptors. So, some of these can already take into account some influence that are not necessarily feed forward, but also we are doing work to enable our models to better reveal also non-feed forward, so maybe top down or feedback processing. And I explain briefly what I think we plan to do. So once is that in our model, we include more and more the effect of neuromodulation. I don't know if you call it feed forward or feedback, but definitely it's not a sensory input. So, and essentially we have version of these that either have dopaminergic or noradrenergic. Sorry.
But what would be the time course of a feedback signal in that case? Because
I don't know. In real data, for example, for noradrenergic neuromodulation, we found that there was, through model-based analysis of data, modulation of the sensory, so input-output sensory gain. So the relationship between the strength of the input stimulus, like somatosensory stimulus, and cortical firing on a time scale, of hundreds of milliseconds. So essentially, we found that the locus ceruleus would drive oscillation of the range of about these 10 hertz or something, and they would at certain phases of this oscillation either enhance or decrease cortical modulation. So some of those sections would be very rapid. And also what we are doing so it's essentially of the kind of dynamic time scale that you will see with electroencephalograms, not maybe with fMRI. And but also what we are doing at the moment is first, we haven't done much work on this, but I think we are starting. We would like to extend these models to not only have recurrent connection and feed-forward inputs, but also to have interaction between several areas. And in this case, you can generate slower oscillations than the gamma that we consider, and you can also fit it to, for example, magnetoencephalography recording from multiple areas to infer essentially also this kind of processing. And we also did some work with information theory to develop our tools to map information transfer, not only like in Granger causality, where you say area A is sending some message to area B, but also telling area A is sending information about choice not related to stimulus, about stimulus, about if it is stimulus, which is, I don't know, multisensory, this is color, this is shape, this is sound, or whatever. So, and it works similar to the one that I showed, but not for information representation, but for information transmission across areas. And I think once we do that, we have an empirical set of data that we can use for modeling. So like in this model where we model information representation, we would like to model information transfer with the biophysical plausible model, and to see as it for information representation, there are essentially pathways that are clearly explained by one or the other. For example, with Tobias Donner, what we are beginning to find is that we can prove that signals, for example, in high frequency, in the high frequency range, seems to carry, as already reported by Pascal Fries, feed-forward information. Feed-forward information, so from sensory areas to higher areas. But also we can prove that this stuff is about the sensory stimulus features and not about choice. And on the other way around, we found that signals in other frequencies carry information from higher order areas to lower order areas. And this is specifically about features of the choice that are not related to the stimulus. So I think, so again, we need some work. So probably the paper about this will come out in a couple of years. But the idea is to apply this very same approach. So detailed analysis of information transmission with non-parametric models, and then detailed modeling of the most salient features, also doing the interaction across areas. And okay, I don't know if this is clear, but I don't have much to say. I mean, we have done some work, but Pablo, that is listening to this conference, will have a lot of work to do on those issues. And okay.
Okay, thank you. So any other questions? Otherwise, I have one. Okay, let me ask. Concerning, I just a curiosity about your data pool. Sorry. There is a question. No, okay. So just a curiosity about your data. So when you show or investigate the information content of let's say low frequencies and gamma in the gamma range. So basically you find out that these are, if I well understood, containing different kind of information. And so there is, of course, this, I have at least in the background, this general belief that the low frequencies are carrying more, let's say, information regarding long range connectivity functions of the brain, and whereas gamma information is more carrying local processing information. Is it true, or do you have additional evidence for that, or did you further investigate this spatial aspect? Did I miss something?
This data, the collaboration from the Logothetis lab analyzed one area only, so primary visual cortex. And in that case, I think we were able to show that these low frequency oscillations that are traditionally considered to carry, for example, feedback signals or essentially signal expressed by the interaction between either, several cortical regions or cortical and non-cortical pathways. For example, slow waves involve corticothalamic interactions and so on. So not only those low frequency signals have that kind of stuff which is traditionally reported, they also contain feed-forward information about the stimuli. And the reason is that natural stimuli vary exactly, with the most power on those time scales. If you analyze very carefully data that are recorded essentially from inputs, movies, image, or also movies taken from positions that are compatible to the eyes of humans. People have done all this kind of analysis, and because of the laws of physics and the distance between the objects, most of the stuff happens exactly at these low frequency bands, like 1 Hz, 2 Hz, or whatever. So most of the salient and ecologically important natural variations happen at that particular scale. So what we have added to this traditional interpretation of this low frequency band is that it is not true. It is true that from other studies that they reveal and express something about complex multi-synaptic loops between brain areas, and also include feedback signals. But it is also true that they can carry feed-forward information about some very important aspects of our environment, that is essentially the natural variations of natural stimuli. And here I focused on vision, just to make a talk coherent with one subject, but also we did a lot of work both with monkey data and also with human magnetoencephalography with my colleagues in Glasgow, especially Joachim Goss and Christoph Kaiser, that now is in Bielefeld. We did a lot of work also on auditory stimuli. So essentially what is generalized from vision to auditory cortex, auditory stimuli, is that if you present a natural sound, such as speech, monkey vocalization, noise made by moving objects and stuff like that, there is a lot of signal, a lot of information in the low frequency envelope of these sounds. And this low frequency envelope entrains neural activity and encodes information about the time course of the sound. So this seems to be a relatively general phenomenon. And the point is that, a lot of stuff in outside world that you need to know to produce useful behavior happens exactly at that frequency band of 1 Hertz, 2 Hertz, 3 Hertz, 4 Hertz, whatever. So, what we have added to this, we and others, of course, we have added to this is that the discussion is that low frequency bands are not the exclusive kingdom of feedback interactions or stuff like that. They are also influenced a lot by feed-forward signaling, because they carry information that you wouldn't get from the spike rates.
Okay, thank you very much.
And also, as I said when I replied to Maurizio, I have not presented any work on this, but we are just starting, and I think we have some preliminary data, but not a huge amount of results, work to extend this to interaction between multiple areas. And with the magnetoencephalography, this is something that you can do reasonably well. And so we are trying to essentially extend these information theoretic reasonings before the modeling, and then modeling on the most important information theoretic exchange that you get between areas to understand the low frequency oscillations and feed forward and feedback processing across several areas.
Thank you. Thank you very much. So is there any other question? Otherwise, I will give back the floor to perhaps Atikur, no?
Can you hear?
Yeah. No, yeah, can you speak?
Can you hear me now?
Very low, yeah.
Oh, very low. Okay.
We have
Hello?
yeah.
Okay, so it's not about question, it's just like my query that, you have one of the sponsors who are working on autism. So, yes. But in your presentation, you did not put much information about this, definitely. But my question is that this kind of research and autism, how do you direct, or what kind of study it's going on? I'm not related to that, but I have some work on autism in different domains. So that's why I'm interested to know that your work and autism, how you can connect.
Yeah, okay, so I tell you, the part of this work, the latest part of this work trying to infer parameters such as the ratio of excitation and inhibition directly from neural recordings was was funded by a seed money from the Simons Foundation for Autism Research. And the reason is that they wanted some kind of quantitative tools to estimate excitation and inhibition ratio from the human brain. And the reason is that, as I'm sure you know, many theories of autism postulate that there is an imbalance of excitation and inhibition, and that, this is at the basis of essentially of some of the, the behaviors observed in autism. And so they just wanted a tool for this, but because there is evidence from cellular level data and others that there is some basis to this hypothesis. So they funded this, and one of the reasons why we do that is that in the end we don't only want to invert or estimate parameters, invert recording, estimate parameters during tasks in control subject, understand how the human brain works as you do tasks, but also we would like to somehow differentiate neural parameters between control conditions and for example autism or schizophrenia and so on. And we have already used this kind of stuff in autism. We had a paper in eLife with Mike Lombardo and Pablo Martinez and also Alessandro Gozzi, where we use this kind of tools applied to fMRI data. I didn't say that, but we also did some work to model how all of these would translate to interpret fMRI data. And basically there, I think we were able to show that, our methods would predict certain pattern of excitation and division imbalance in autism with respect to control subjects and differences between men and women, and also correlation of the level of excitation and inhibition ratios estimated with our algorithms with certain behavioral aspects such as camouflaging behavior, which is something made by, females with autism. So my understanding, camouflaging means that essentially these people essentially try to change their behavior to camouflage the behavioral deficit that would arise as a consequence of autism. So I think this is a long-term plan. We are doing it, and here at UKE, the University of Hamburg Medical School, we are working with the psychiatry department to use these tools to estimate imbalances of excitation and inhibition either in autism or in schizophrenia. So, one of the goals of our work is ultimately to be able to help essentially the interpretation of EEG or MEG recordings or fMRI recordings to understand better the neural basis of some diseases. And this is also, we see also a validation of our method, because I think from what I showed very quick at the end, we have some proof that our method can discriminate between different manipulations that we do. So if we increase with the drug or with also optogenetic, we did and so on, excitation over inhibition or vice versa, then we give these EEG recordings or LFP recordings to our algorithm, and the algorithm can tell what you did. But it is possible that the manipulation that we do pharmacologically or optogenetically maybe are larger than the differences between a healthy brain and the brain with autism. So what we would like to do, and we have some encouraging results, but again, nothing really, it's ongoing work, that, the method has enough power to detect differences between essentially autism and controls. So this is, one of the reasons why we started this, and why the Salmon Foundation agreed to help us starting this research.
It's a wonderful. Thank you.
Thank you very much. Do you have a question? Any?
Yeah. May I just ask about one curiosity that Stefano is here. So, well, the different scales, the data that we get in different scales, for example, from cellular to imaging. So you have vast experience on all of these different scales of data, starting from single cell data to network data in terms of spikes, as well as local field potentials, then EEG, and then fMRI and all these kind of things. So these different scales actually represent different levels of network activity and denote different specific activities of the brain. Now, in terms of, let's say, if we are thinking ahead in the future and thinking of having some diagnostic methods which people can use for, let's say, clinical diagnosis of certain disease, for example, understanding autism, let's say, that at an early stage, whether someone can detect that whether a baby who is born, whether there are some traits of autism in that particular baby or not. So how, well, from your experience, do you think that all of these different scales of recording can contribute towards that particular goal of having a system where the clinicians will be able to detect or at least predict with certain accuracy autism maybe in the future?
Thanks, Mufti, for the question. I think it's a very important one. And the first thing I would like to say is that I'm not a medical doctor, so I'm always a little bit embarrassed when I have to talk about diagnosis and so on, because of course I know nothing. And I mean, people like Maurizio, I think give a real view about this. But from essentially our small technical point of view, I mean, my impression, and please, Maurizio, if you are still there, correct me if this is not true. There is a lot of room for improving diagnosis and understanding, not only monitoring brain data over time and so on with different recording modalities like EEG or fMRI and so on, but also being able to monitor behavior over longer time scales and on a more quantitative basis. I think, for example, of stuff that you can understand from movements or of how individuals interact and so on. And I think all the psychiatric diseases have aspects that are related, for example, to interactions. And I mean, as technology goes on, and we'll be able maybe to record, I don't know, say movements or behavior of people in an automated way for longer periods than those that the doctor can see them in the clinic, and then those can be analyzed quantitatively. I think this is, a super important domain for future quantitative research, also from computational neuroscientists and so on. That would be my impression. But as I said, I'm not a medical doctor, and this is, an impression that I get talking to various specialists and various both cognitive scientists and doctors. And I think there is a lot of room to contribute to that.
Okay, thank you. Yeah.
Thank you very much, Stefano. Yes. Well, I'm a medical doctor. We are kind of like share your opinion, by the way.
Okay.
Anyway, so I think we are, unless there are other questions, we are at the end of this keynote lecture and discussion phase. So I would probably like to give the floor back to Mufti for technical directions, let's say, and then back to Professor Zong, perhaps. Yeah. So Mufti, please.
Yeah, thank you very much, Stefano. Well, right now, after this session, we have an extended, networking session. Unfortunately, well, one of the disadvantages of having these online conferences are that the main interaction, the reason of conference is missing here, which is networking and interaction, and trying to get people during the coffee and discuss few things. Well, generate new ideas and create new network. So after this, we have 30 minutes to actually continue this discussion, and this room will be open. So if someone wants to grab a virtual coffee in that particular sense, can grab a coffee and continue the discussion here. So the next keynote session will start at 10:30 UK time, which is like 33 minutes from now. So we have this 33 minutes for any virtual discussion or virtual coffee, get together, networking, connecting with each other. So if you prefer that this time is not recorded, because it is something which is probably going to go the personal level, I can pause the recording and restart the recording once we come back into the session. Okay, so now the recording is paused. So we have around like 33 minutes now for informal discussion and virtual coffee. So, well, next year, if you join us, probably we'll be able to offer you some real coffee, hopefully. Italian coffee, yes, of course.
Not British coffees, I hope.
Well, it's going to still happen in Padua, hopefully, next year.
Okay, so see you in half an hour, and thanks again, Stefano, for attending for the lecture.
Thank you. Yeah.
আসসালামু আলাইকুম শামীম স্যার, কেমন আছেন? Maybe we
yes,
can
please.
also speak in Bengali. Is it?
So Stefano, well, you have vast experience in also working in different environments, different countries. Now recently you moved to Germany. Well, what is your impression in terms of research and your experience in working in different countries? That how do you actually feel that who are contributing in which fields, in which way? So if someone wants to work in a particular field, do you have, especially thinking of computational neuroscience, do you have any specific guidance for some of the upcoming new researchers who are here attending this session?
I mean, there is a lot of exciting research all over the world, so it's difficult to pinpoint, I mean, different strengths, different nations, but I mean, of course, the United States, places like Stanford, Columbia, Harvard, MIT, and so on, and many other universities, there is a lot of research in computational neuroscience at all possible levels, from cellular to cognitive and so on. And also, I mean, in Europe, there is a lot of very nice work. I don't know, I can speak for Germany or for Switzerland, UK, France, Spain. I mean, there are so many. I think Mauricio, for example, there's a lot of collaboration with the groups in Spain, like Gustavo Deco. So there are, I mean, so many super nice groups in so many different countries. And also, I don't have a huge amount of experience collaborating with people in Asia. I collaborated with the International Research Center for Computational Neurointelligence at the University of Tokyo, and I mean, they seem to have excellent strengths. And I know also my friend Nikos is moving to China, and they have an incredible research center over there in Shanghai. So I think, I mean, there are so many exciting places. Also, Partha Mitra will be a speaker later on, also has a lot of work, I think, in Madras. So I think, I mean, people can choose, I mean, young people can choose between a lot of very different environments. And I mean, I'm sorry if I say something maybe trivial, but also sampling more than one environment, I think it's extremely useful. I mean, for example, you moved, you worked in Italy and also in UK and so on. And if you have the opportunity to move around a little bit, I think you can learn a lot about from the personal point of view and also from the scientific point of view. So I mean, I was very happy that I had the opportunity to travel.
Yes, well, absolutely. Well, you have a very colorful profile, actually. Well, because when I was a PhD student, that was back in 2008, well, with Stefano Vassanelli. So, well, you were probably at that time in Glasgow. So, yes. Yeah, so at that time, well, we used to read your paper in Glasgow. Then sometime I saw that you were in Manchester.
That was before. I mean, so the last 10 years, I think I moved from Glasgow more than 10 years ago, I think, and then I was in Italy for about 10 years, and then I just moved to Germany, I mean, like 2 months ago. So,
yeah, fantastic.
But I had the opportunity also to go very often to the US, to Harvard, for example, for collaboration. So I kept, even staying in the same place for 10 years, but I try also to visit various centers around the world to learn more and establish some networks and collaborations. This is also nice. I mean, if some people cannot travel or cannot move too much, maybe for family reasons and so on, but it's still good maybe to be able to, maybe with short visit and so on, get some experience in other places.
Well, now this question might be very trivial. What, in your opinion, is actually the key to such international collaborations that you're holding? Because you are having many international collaborations and successful ones.
I don't know. I think the key is, I don't know, in general with collaborations, you try to understand what are the key questions and unsolved problems of the other person. I mean, sometimes I think, for example, for a young computational neuroscientist, I think, I mean, people are strong with their algorithm, with their technical knowledge or their knowledge about the mathematics and the theory. And sometimes the temptation is just to try to essentially, in quote, sell to the collaborator, if it is, for example, an experimental collaborator, what we have ready. But I think this works to some extent, but what works better is instead you try really to understand what is the thing that the other person really needs to do to elevate the conceptual level or, I mean, of his or her research. For example, experimental neuroscience, you know, we want to answer this question and what would we need to do that? And then try to start from that. So if this is your problem with my background, what can I contribute? How can I help you solving the problem? And at that point, I think something comes up that neither of the two people would be able to do in isolation. And I think, you know, that works. So essentially, you know, you have your strength, you have your background, and be proud of it. But at the same time, try to understand what I mean, your potential collaborator really needs. So, and try to address that.
Yes, indeed. So we also have now here Professor Jiang, so who has joined us. So Professor Jiang is from China, and China being one of the key players also in brain science. So Professor Jiang, do you want to share your views in terms of where the field is going, maybe in terms of brain informatics?
So in fact, now another conference. So I will go to have a dinner and then come back again. So maybe after my talk, I can share some response to your question or some other question.
Okay, absolutely.
So yeah. So now we should move to have the dinner.
Okay, sorry.
So okay, see you later.
Okay, see you. Yeah.
Also, I think I need a short break. I'll be back in a couple of minutes.
Yeah, sure. No problem. Yeah.
Hi, Michele. Good to see you.
Hi, Wolfram. It's a pleasure to see you. Zoom is not the same as in person, but it's enough.
Good.
Yeah.
Hi, Stefano.
Hey, Wolfram. How are you?
Good, and you?
Okay, yeah. Getting to use with the inflexibility of German administration. But,
Yeah. So you're already in Hamburg?
yeah, I moved during the summer.
Okay, great. Congratulations.
Thank you.
Welcome, Michele and Professor Wolfram Gerstner.
I moved in.
Hi, Mufti. Nice to meet you here. Yeah, you've only corresponded by
glad
email.
Yeah, very glad to have met you. And well, personally, thank you very much for agreeing to deliver this keynote. Very much appreciated.
Sure, it's a pleasure. Yeah.
So we would like to play the video when it will be time, yeah, in 4 minutes from now, well, after the introduction by Michele. So then we will play the video, and during the video also we'll try to collect some questions if the audience has any question on the go. So we invite them to write them on the chat as well. So we'll try to collate them and then have those discussions once the presentation played back is finished.
I can even answer on the chat questions during the presentation, or if it's technical questions. Yeah.
Okay. Just a second. Well, someone is probably at the door. This is the worst part of the online presentations.
Michele, you're part of the organizing committee as well?
Yes, but honestly, I think Mufti did everything. I'm just helping now, but I didn't do anything else. I have to admit.
Yeah, no, but it's nice and
it's a very nice program. It has been very, very interesting.
Yeah.
I attended a couple of sessions but yeah.
Yeah.
This was the most interesting question, of course, because I had to be here. No, and it was because of your talk.
Yeah, thanks.
And of course, personal thanks, Michele, for making the time.
It's an honor. What was possibly difficult was to get the right time, but because you are here and Wolfram is here, I'm in the right time zone somehow.
Yeah. So I also typed in UK, London. What's
Indeed.
Yeah, well, that is something which is actually a little bit difficult. So we thought that maybe if it is just GMT, then things become easy. But then GMT +1 is a little bit confusing, this British summertime.
Exactly. But we are also on summertime. But then in October, there's maybe some shift for 2 weeks, at least with the US. It's like this. You don't know exactly whether it's 0 or whether it's 2 hours. I have no clue.
Exactly. Yeah, there is this particular period is a little bit confusing. Yeah.
Yeah.
I'll just check that if the video is visible, though I will disable it to allow Michele for the introduction part. So
Looks maybe a tiny bit squeezed. Okay.
So shall I increase the size? Does
sure.
The aspect ratio, you mean?
Aspect ratio, I think it's, but I'm not sure. Maybe it's about right. But it looks a little bit squeezed, but it's the old format.
Yeah, because it was not the widescreen one exactly. So it was not the widescreen one when I received. Probably during the recording, probably it might have changed.
No, the recording was fine because I did it directly in the
So this is the file that you submitted. So it is directly the file that we received in the Dropbox.
Yeah. So it's, can you?
So I think that, well, let me just disable that so that we are right at 11:30 here in the UK time. So we are at keynote session 3. So it gives me immense pleasure to welcome Professor Michele Giuliano to chair the session, please.
Thank you, Mufti. Welcome to everyone. It's a great pleasure and privilege to introduce you the lecture of Professor Wolfram Gerstner. Professor Wolfram Gerstner studied physics at the universities of Tübingen and Munich, and he received a PhD from the Technical University of Munich. He worked in the US, first at University of California, Berkeley, as well as at Brandeis University. And since 1996, he is the director of the Laboratory of Computational Neuroscience at the EPFL, where he is full professor with a joint appointment both at the School of Life Sciences and at the School of Computer and Communication Sciences. His research interests are very broad and include the study of models of spiking neurons, the dynamics of spiking neural networks, and spike time-independent synaptic plasticity. More recently, he became interested in generalization of Hebbian learning in the form of multi-factor learning rules and in the role of surprise for learning. He is also the recipient of the Valentino Breitenberg Award for Computational Neuroscience in 2018, and he's a member of the Academy of Sciences and Literature of Mainz in Germany. I give the floor to Professor Wolfram Gerstner, whose presentation is entitled Neo-Hebbian Three-Factor Rules of Synaptic Plasticity, from Reward to Surprise. Thank you.
Thanks, Michele, for this very kind introduction. Thanks a lot. It's a pleasure to be here. Thanks, Mufti, for the invitation. And so the procedure is that it's pre-recorded. It will last 45 minutes. During that time, you can ask questions on the chat. And at the end, we have 10 or 15 minutes for the question session.
Okay, so I'm now playing the recorded video.
Welcome to my lecture on Neo-Hebbian three-factor rules of synaptic plasticity, from reward to surprise. I'm interested in learning. Now, learning happens at many different levels. For example, I like table tennis, and I've learned to play table tennis by getting the feedback from my opponents, from where the ball lands. And feedback comes often in the form of rewards. So learning to ski, to bike, to play table tennis and many other things can be attributed to learning by reward. But that's not the only situation. There are also situations where there's no reward at all. For example, we may walk around in a city just like that and explore the environment and build a mental map. Or we might be on the highway. So I was traveling on a highway some time ago, and always in the right lane, safe lane, and cars were passing by on the left lane much faster than me, and suddenly there was this little red car who passed by, went in front of me, and immediately afterwards stepped on the brakes. So I was like this. And if I now ask, what do I remember from this trip? It's this one little red car. So it's this learning by surprise, learning at moments of intense emotion. Learning happens in the brain. It happens in the neurons of the brain, and more precisely, it happens at the synaptic connections. So if a spike comes in at this point here, then this spike will cause this spike coming in here will cause a response, and this response can be measured, its amplitude can be measured, and learning means a change in the response amplitude, a change in the connection strength. A classic view of learning, of this change in connection strength, is Hebbian learning, which basically says, well, if we have a neuron that sends out spikes, a presynaptic neuron, and another neuron that receives the spike, the green neuron here, neuron I, then if the two are active together, then you get some kind of change such that the synapse is stronger. So connection strength increases with joint activities, and there are many experiments that have confirmed this. So here are two schematics of how this could work. The first one is the green neuron sends out spikes, the orange neuron receives spikes and also sends out spikes. So we have coactivity, and then it's the synapse of the green neuron that is strengthened, but not the red one, because here there are no input spikes. Now the orange neuron, the postsynaptic neuron, doesn't have to fire. It could also just show some depolarization of the membrane, stay subthreshold. It would still be considered as co-activation. I'm a theoretician. So as a theoretician, I may ask, what is a general way to write down this kind of learning? Well, I look at the weight, Wij from J to I, and say this weight can change, and the change may depend on the weight itself, and then according to Hebb's idea, it should depend on whatever comes from the presynaptic neuron. There could be spike arrival at the synapse, it could be a trace of neurotransmitter left at the synapse, or something else. And then it also has access, this synapse has access to the postsynaptic activity. That could be the back-propagating action potential. It could be a voltage at the location of the synapse, say some low-pass filter trace or calcium, which is something like this. So this looks like a very, very general framework. And now I would like to claim that this framework is still not general enough. Because what's needed is the third factor. I say third factor because there's always a first factor, we need presynaptic activity. A second factor, we need postsynaptic activity. And then we also need some form of neuromodulator. And importantly, this neuromodulator may come with a delay. It may come at the same time, but it may also come with a delay. And here are the experimental results. The first one is in striatum from the Kasai lab. You have pre and post together over 1 second, and then after another second or so comes dopamine, and with 1 second delay you get a positive change. If the dopamine comes a bit earlier, the change is bigger. Simultaneously is also good, but it shouldn't come too late or too early. Now in cortex you have something very similar, pre and post together, and then you give norepinephrine with a delay of 5 seconds. It gives a positive weight change. Or you do post before pre at the red synapse, and you give serotonin 5-HT, and then you get long-term depression. So the neuromodulator may come with a delay of 1 second or even 5 seconds, depending on the cortical area. So how can we now take this into account? Now I make my framework even more general. I say the weight change depends on the weight, on the presynaptic activity, on the postsynaptic activity, and on the third factor. And how could that be? And how would that connect back to these Heppian ideas? Well, take your favorite Heppian rule. For example, take STDP. So we have here a presynaptic spike, a postsynaptic spike a little bit later. So pre before post, that's good, that could give STDP. But now this Heppian condition, this STDP condition only sets a trace. The trace will decay with a time constant of 1 second. Why 1 second? Well, 1 second, if you think about it, is sort of one elementary movement if you try to catch your object. And normally this information, this eligibility trace, this Heppian coincidence detection memory will decay over 1 second unless you have this success signal. And the success signal is reward minus expected reward. It could be dopamine. It's spread out all over the brain. And this success signal finally means that the weight is changed, that the eligibility trace is written over into a weight change. Why is this good? Well, think of this little mouse in a tea maze. In this environment, there's Swiss cheese on the left-hand side. The mouse moves forward. It's at this decision point and decides to move right. Okay, at the decision point, there are place cells that are active, and then it takes an action plan going to the right. There are other cells that get active, and now the Heppian condition says Well, the two cells are active together. Therefore, we should have a weight change, but now I say it's not a weight change, it's just setting an eligibility trace. And then there's no success, there's no Swiss cheese. The eligibility trace keeps the memory over a second, but then it disappears. A little bit later, the mouse is again in the same environment, it moves up to the same place, and now it decides to go left. In this case, again, I have co-activation of pre and post, and now we have the success signal, and the success signal means that this synapse now is really strengthened, and that implies that the next time the mouse is again at this location here, then it's more likely to move left again, it's more likely to approach the cheese. So I said success signal. Success could be signaled by dopamine. It's a long, very successful, very influential story of Wolfram Schultz and colleagues, Peter Dayan, for the link to the theory. And this theory, this idea of three-factor rules can also be linked to the formal theory of reinforcement learning. Suppose we have success is reward minus expected reward, and this is the third factor. Then I can pick up the book of Sutton and Bartow and look at TD learning, for example, Sarsa, and I realize, well, it's exactly this kind of rule. It's a three-factor rule once it's interpreted in the form of neurons. Policy gradient, another of these classic and reinforcement learning algorithms, also mappable to a three-factor rule. And so here is one of these examples that I made up. So here's an environment. It's not the T-maze. It's a bit more complicated. There's a barrier, the red barrier somewhere in the middle, and then in the very middle is the green reward location. And so it's a continuous 2D space, and this continuous state space is represented by spiking place cells. The place cells sit here in this region here, and each cell is responsive in a small region of the environment. And at every location, several cells respond, so I have some distributed code. Then I have, on the left-hand side, a ring of actor neurons, and these actor neurons have centers around connectivity, so nearby neurons excite each other, far away neurons inhibit each other, so I get a blob of activity, and this blob of activity would indicate the current direction of movement. It would indicate the current, it would implement the current policy. On the right-hand side, I have an independent population of stochastically spiking neurons, and they form the value map. On the left, it's the actor neurons. On the right, it's the critic neurons. And these critic neurons calculate the value. Value is high if you're close to the target. You have to learn this. And learning is done by sending a TD error, a difference of values. And this is used now in a three-factor rule. And it's the same three-factor rule for all connections, those from place cells to critic and also those from place cells to actor. And let's now see what this does. Here's the environment again. We have 4 different start positions. The goal is in the middle. And you see at the beginning, it takes a long time, 50 trials, before the target is found for the first time. The first trials are the dark blue ones. You see it's this weakly approach. It's basically a random movement towards the target, until you find by chance the target. And then already after 10 or 20 trials, the latency is down to 10 seconds. And if you look at the traces, you see that they more or less go straight to the target. And this is achieved with this three-factor rule in an actor-critic architecture. So yes, reinforcement learning is possible, and reinforcement learning is even fast. After 10 trials in a continuous state space, continuous action space, you can find the goal. And after some time, you can also read out the type of things that the critic neurons have learned, and they have indeed learned the value map. Let's summarize this part. So three-factor rules are a generalization of HEP rules. We have the two local factors from HEP, pre and post, and then we have one global factor, which is the same for many neurons. And I say a three-factor rule, it's not one rule, in fact, it's a framework. This sets a frame, and there are many different realizations within that framework. Now, in the example I've shown you, the global factor is reward minus expected reward. We link to the theory of TD learning. Now, in the next part, I would like to generalize to several global factors. We have not only dopamine, we also have acetylcholine, noradrenaline, and these could relate to different emotional brain states that modulate learning. I talked about reward, but why not surprise? Something exciting, something good, some progress. And this leads now over to this generalization where we go from one neuromodulator to several neuromodulators. So here again, the classic view. Dopamine neurons sit somewhere deep in the brain and they have ramifications throughout the brain. It's a broadcast signal, near global. It doesn't arrive at all the areas, but very broad. And then we have pretty much the same view for noradrenaline. It also starts somewhere deep in the brain, and it also broadcasts to nearly all areas. Now, a classic view is dopamine is success, where success is related to reward or reward minus expected reward. And noradrenaline may be to surprise or novelty, but there's no fundamental reason that that axis should be perfectly aligned. You can easily imagine some rotation of the coordinate system such that if you turn it, you span the same two-dimensional space. So I claim there's a space of reward and novelty, and if you have two or more neuromodulators, you can cover this space. Now, what can you do with this kind of setup? I made up a little toy example. I assume that there are two types of neurons, the orange neurons and the blue neurons, and then there are two types of neuromodulators, modulator M1 and modulator M2, both of these broadcast signals that arrive all over the brain. And now let's walk over some possibilities. So in the first line, I have a connection between two orange neurons. Let's suppose they are active together. Here are little red dots, active together. This sets a trace. You see the green flag. And then I have the green modulator, and poof, it could be LTP. The same pair of neurons becomes active, sets an eligibility trace, and I have both neuromodulators at the same time. They could cancel each other or even override it to LTD. Now let's look at the connection for orange to blue. Both active together, two neuromodulators that could give LTP. Blue to orange, that could be no change. And then you can add up many more possibilities. So just the combinatorics of the things. I have two types of neurons. I have two modulators, and I have many possibilities. So I get the specificity from the combination of the Heppian factor that says, I pick two neurons, those that are active. And then I have this more or less global signal coming on top, but I have more than one of these. And now if we think that we have 5 neuromodulators, and if you think that we have 10 or so different types of neuron, then we get a combinatorial explosion that allows us to be quite specific to address specific pairs of neurons. In the following, I will focus on 2 modulators and 2 signals, one reward, the other one surprise. We said already, reward is very well encoded by dopamine, and dopamine is linked to surprise minus expected reward. So that would be TD error. Okay? So what is the equivalent for surprise? Well, maybe it's just surprise. Okay, we know how the TD error is defined. It's reward minus expected reward. But how would you define surprise? We know how to stimulate the reward system. You give chocolate or money or food pellets, depending on what type of animal you have in your cage. And now, how would you stimulate surprise? So that's the question that I would like to address in the next two parts of the talk. What is a good theory of surprise? And then what is its relation to three-factor rules? So now let's go and look at surprise. Surprise in the context of three-factor rules. And to do that, I will start with a simple example before we then go towards a theory. And here's the little example. Let me try to start it. Just watch these sequence of images. That's it. So when are you surprised? So what you have seen is that somewhere there was, for most people, something surprising. Now, the kind of sequence you saw was a little bit like this. Suppose images have numbers, it's maybe like this. I didn't tell you what's about, but you cannot help. You start to make a model of what you see, a model of your world. And expectations arise from models of the world, models that you spontaneously make. We always make models. We know that the models are not perfect. And now my claim is that surprise enables us to adapt our models. And here we go. So the hypothesis is now that surprise boosts plasticity. You want to adapt the models. You boost plasticity at the right moment. And in that sense, surprise can play the role of a third factor. And note, there's no reward. I just showed you a sequence of images or a sequence of numbers, and you just watch. You're in a passive mode. You're not searching for something. You don't expect to get a reward. And you don't know what's about, but you cannot help. You make models of the world. So, three questions come up, and I'm not the first one to look at these questions. How does surprise affect learning? And here we claim surprise boosts plasticity, and this idea has come up before. But then what is surprise? We need to look at definitions of surprise, and I will show you a very specific one. Now, and finally, the question is, how does the brain calculate surprise? And this will relate to predictive coding, as you will see. So here's another little example, and I think of this as a task that you can play. This time I tell you what to do. You see on the left here a couple of points, and your task is to estimate the mean of these points. Okay? And while you do this, you realize that actually sometimes there are abrupt changes. It's what's called a volatile environment. So the generative model would be a non-stationary stochastic process. Here it's a Gaussian with fixed mean, and then the mean changes. The variance is fixed all the time. Your task is to estimate the momentary mean, and the way you do this is basically that you go along as the sequence appears, then something changes, and this is where the red little arrows are. So now the idea is that in this kind of task, you don't know what's happening. You make a model, but you should reset your model at one of these change points, at each of these change points. And so this was the actual mean, and you see that there were some big jumps at the beginning. And so I asked you to estimate this mean, the momentary mean, which is this theta here, and you believe is some distribution about this mean. And at the beginning, you just know, well, it should be somewhere in this region here, because this is the scale I show you. That's your prior. And then your belief gets more narrow, but then you have to jump, and it gets narrow again. It has to jump again. And so sometimes when you realize there's a jump, you reset, and you reset to the prior. So the prior is this P0. And sometimes you realize actually it makes sense, your belief gets sharper, and that's when you integrate. Now this gamma is a factor that lets you switch between the two modes. And this is what I call a surprise modulated adaptation rate. And so for large surprise, gamma gets towards 1, and that means you basically just take this term, you reset, and you start anew. For small surprise, you have a small gamma, and then you integrate just like in standard Bayesian integration, and your belief gets more precise, gets sharper and sharper, and gamma is the switching factor, that's the adaptation rate, and surprise makes you switch from one case to the other. So surprise boosts plasticity. Surprise boosts this switching, and this surprise comes out now of a formal Bayesian theory of what you should do in these volatile environments, and we call this the Bayes factor surprise because it's a Bayes factor. It's the ratio between, in the numerator, the probability of the current observation y under your prior belief, having not seen anything before, compared to the probability of observation y under your current belief, pi of t. And then this surprise goes into this gamma factor, and that allows you to switch to either to do integration, normal Bayesian integration under a stationary world, or you do the reset. So you reset your belief to the prior if the observation y does no longer make sense. Now this is exact Bayesian inference, and this exact Bayesian inference is an update rule that's in general, except for very special models, not implementable. But the idea that surprise changes plasticity is more universal, and in fact this Bayes factor surprise plays a crucial role in many approximate methods. For example, we'll look later at a variational method called VAR-SMILE. We can also look at particle filters with n particles, at message parsing with n messages, at published approximations coming from different labs. In all cases, you can identify this ratio, which is the Bayes factor surprise. So the Bayes factor surprise boosts plasticity, and it appears naturally in Bayesian models. But then the question remains, well, how would the brain calculate surprise? And we'll look at two algorithms now. The first one is the Bayesian, and the second one is a spiking 3-factor. And when I say Bayesian, I actually mean approximate Bayesian algorithm. Let me start again with my sequence of images and make it slightly more complex. So here you see the sequence of numbers that develops, and if you stare at this, you realize there are sort of motifs, transitions that repeat. There are other things that don't exactly repeat. The way I generated this is that I started with a Markov chain, Markov transition matrix. From every state, I have 4 possible transitions, and you can imagine these transitions as transitions between states in a 2-dimensional environment. So we would start at 1, 7, 4, go to 12, and then we go to 15, we go to 7, then to 3, to 6, to 1, and so forth. And this would be my sequence. And then occasionally we have a switch and we go to some other configuration. It's the same states. So if you want, the sequence consists of the same numbers, but the organization is different. So again, I have a stochastic process that itself changes from time to time. It's a volatile environment. Now again, hypothesis, we make a model of the world, we cannot help, we do that all the time. We are surprised if the world changes, and then surprise triggers relearning. So now we make an algorithm, we construct an algorithm which is called VAR-SMILE for Variational Surprise Minimization Learning. And the way it works is the following. We estimate the possible transitions, the allowed transitions. We have n images corresponding to the n states. N is known. It's an arbitrary configuration, not necessarily a two-dimensional environment. And if the world changes, you just forget your earlier estimate. Now, you are surprised if the world changes, and this surprise is the base vector surprise. So you compare your prior with this estimate of the transition matrix. How do you make this estimate? Well, you count the transitions in a forgetful manner. So this is the forgetting term. You have a leaky integration, leaky count. This is the count for the transition from S to S prime. This is the count one step earlier. You update it if you arrived in this state S, and else you just keep your count. You don't touch it. And this transition matrix is just the count for this transition from S to S prime compared to all other possibility, and epsilon and n are sort of normalization factors. N is the number of states at the beginning. Epsilon is a regularization factor. And so here's your discount term, your forgetful term. If you are surprised, then you have a large gamma close to 1, and that means you reset your counts to 0. So here's now in this environment that I described before, you just see these images or these sequences of numbers, and we compare this algorithm that's basically a surprise modulated online leaky count algorithm derived in a variational framework, and we compare this with a optimal Bayesian change point detection, online change point detection, and you see they are very close. The error is very similar. What's the error? Well, we know for this kind of environment, we know what the transition matrix looks like. We can look at our estimate and compare the two, and this is just the mean squared error to the ground truth transition matrix that is plotted up here. So, conclusion so far, this algorithm, VAR-SMILE, is an excellent approximative algorithm. But then the question remains, well, is this also biologically plausible? So biologically plausible for me, and this leads back to the topic of the talk, is that, well, somehow there should be a 3-factor learning rule. I have connected neurons, and then surprise comes in as a 3rd factor. So this is VAR-SMILE. I can sort of see, well, it's a modulation, so the surprise plays the role of a 3rd factor. We can say surprise boosts plasticity, makes you forget, big surprise makes you forget your count. The forgetful count of transitions could be stored in the synapses. Then I could end up with a Happian learning rule with 3rd factor. Well, I could. Then let's do this. So here is how we do this. We say I have these transitions between different states from state 1 to state 13, say. I'm currently in state 13. This gives my current observation, which is represented by 80 spiking neurons. Each image, each number corresponds to 100 milliseconds. And in a buffer, I keep also my previous image, which also corresponds to some spike trains of 80 neurons. So it's a n-hot coding. It's always a couple of neurons that are active in each state. And then I have here in the red box, I have an EI mismatch network. So the idea is that I have inhibitory plasticity that does EI balance, that enforces EI balance. And then if you see something surprising, this is indicated by an EI mismatch, and hence by a big activity. This big activity is picked up by the 3rd factor, and that's then sent back as a 3rd factor signal that modulates synaptic plasticity. And here in gray, you see the activity of the network. What you should see is that sometimes it goes up in big jumps. And then we have on the left-hand side the error with either the three-factor rule network, where I have modulation of plasticity, and that's the red trace, or the same network, same layout, but no modulation by the third factor, just a constant plasticity, and then you are in the green error mode. And you see that the green error doesn't go down as much, and moreover the green error is also pretty high at the transitions. So we can compare overall over a long simulation. And again, the Bayesian change point detection is gray. The var smile, which was my approximate algorithm, is in black, and it's very close. And then the red is the rule, the spiking network with three-factor rule, and it's very close to var smile. Whereas if I don't do this modulation, if I don't have the third factor, then the error is much bigger, indicating that it's much worse. Therefore, conclusion 3, the surprise calculation is possible in a spiking network, and the three-factor rule can be implemented in a spiking network, and the third factor is sort of the EI mismatch, is the overactivity, the overshoot of the activity that indicates something now is unexpected, therefore I'm surprised. So now we have a theory of surprise with three-factor rules, and I started off with these examples. We did a little bit of psychophysics. I made you watch this video, and I said, well, you're surprised. Can we do that in real psychophysics experiments? So now let's look at learning, reward and surprise together in a behavioral paradigm where you have to find the goal. Let me just go back. In the first part of the talk, I said, well, learning happens with TD error as the third factor. So let's look at these kind of transitions. In some maze, you have different states, you can make transitions, and there's only one reward. The reward is at the end. And now we said there's a critic. The critic would calculate the value of different states. This is now a discrete situation, and the critic sends out this TD error signal, which is the third factor, delta, where you compare the reward with your values. And then we say the values of this earlier state, n-1, is updated proportional to delta. And now let's check this out. Suppose all the v values are initialized at the 0. We are really at the beginning. We are in the first episode, first exposure to this environment. You know nothing. So the only reasonable way to initialize things is to say we put everything at the same value, for example 0. And then we update these v values with delta. And I gave you the delta, and now you walk along, so you walk here, and then you walk down, and you walk here, and so forth. Each time you compare the v value of your current state with the v value of the previous state, it's 0 minus 0, there's no reward, so delta is 0, therefore there is simply no update. TD learning does not happen before you find the goal. So TD learning only starts the first time you reach the goal, which would be the end of the first episode. And my claim now is that the transitions are somehow learned without reward, just by watching what you see. And let's now do a little psychophysics experiment. And this is an experiment we really do. I tell you, it's 10 different states. These are just clip art images. And you have 4 buttons. Now you sit here in front of your computer. So your buttons should be, you make a fist with your left hand, you make a fist with your right hand, and then you tap your left knee, you tap your right knee. So you have 4 different actions, and now we just watch the different states. So the first state is the first image, and you see it. Okay, now you take your action. Take one of those 4 actions. Thanks, and you arrive at the second image. Take one of those 4 actions, and you arrive at the next image. Take one of those actions, and you arrive at the next image. Take one of the actions, you arrive at the next image. But wait, Have you seen this image before? How would you choose your next action now? Would you take the same action or a different one? So make your decision. You arrive here, and after many, many steps, you will find the goal, which is just a very specific image. So this is the layout of the environment. You walk through this sequence of images. The buttons are indicated with these little circles, gray circles. You press one of the buttons, you get to the next image, and after some time, you arrive at the goal. You don't know what the layout of the environment is, but it's like this. Now you always have one action, always a different one, that leads you forward, but then you have also 2 of the 4 actions that lead you down in what we call trap states. And as a result of these trap states, it actually takes in the experiment a long, long time to reach the goal. So basically, participants have 100 actions or more before they encounter the goal for the first time. And the first episode ends with the goal. So, first episode is long, but then in the second episode, episode 2, you go straight to the goal. Basically, maybe you make one mistake, you make one little loop through the trap states, but you go to the goal. So you have learned your actions, maybe you have even learned your transitions during the first episode. And now we play a trick. After 5 episodes, we swap states. Now, state 3 and 7 have been swapped. So if you go from 2 to 3 here, you would now go from 2 to 7. You would see this image for 7. And that's the moment you are surprised because you learned the model of your environment. And then you see that in the first episode after the switch, the big red bar, you still have quite a few actions, but it's much quicker than at the very beginning. So it's a rapid relearning, and we can show by modeling that without surprise, you wouldn't be able to relearn as fast. And so what we use is this surprise modulated update rate, where here is this factor gamma, and on the bottom axis, on the horizontal axis is the surprise. You have seen this graph before, and thanks to this surprise, you can readapt to the new environment after the swap of states. So here, the surprise modulates the learning while we run a reward-based task, while we run a reward learning task. And what we find is that action choices of human behavior are best explained by a model-free reinforcement learning with eligibility traces, but then a surprise modulated learning rate. Now, this might be confusing for people who are expert in reinforcement learning. So here we have built a model of the world. We know the transitions. Yet, it seems when we fit different models, people don't use their model to plan actions. It's not used for planning. The model is just used to detect moments of surprise. And then we have the surprise modulated learning rate. But for the rest, you run model-free with eligibility traces. So, let me sum up. I've talked about neo-Heppian learning rules. These are Heppian learning rules that have 2 Heppian factors, pre and post, and then a third factor. And this third factor can be a reward, but also surprise, or something else. Whatever you like to have as emotional states will correspond to neuromodulators that could modulate, that could change synaptic plasticity. The time scale of eligibility traces can be measured. It's 1 to 5 seconds in slices in these measurements between neurons of synapses. We also can measure it in behavioral experiments. We also find a few seconds, more in the range of 10 seconds. Then I showed that this reinforcement learning task is fast. After 1 episode, you're done. And that's thanks to the eligibility trace. And then we still, in the same environment, we have surprise. Surprise modulates plasticity, it modulates learning. We can show that this base factor surprise is exact in volatile environments and it's implementable in spiking networks. Let me make just a little detour before I close. I talked about three-factor rules. Three-factor rules are a framework. It's a conceptual model. Now, if you look at the history, you see that over 50 years ago, it started with the first article of Crowell. It just said, okay, there are moments where you would like to say, learn now, this is important. And then comes the whole history, starting with Klopf and then Bartow and Sutton and Bartow, that did neuronal models around plasticity under rewarding situations. And then this changed to TD learning with Watkins, with Peter Dayan, and then came policy gradients with Williams. Then came the first link back to biology with Wolfram Schultz together with Peter Dayan. Then came applications in various groups to different biological settings like Hippocampus model. Then people started to look at spikes. And then people said, well, you could even do a little bit of supervision with these three-factor rules. So the three-factor rules really started as a conceptual thing on the side of theoreticians. And then it was around for 2 decades before the first experiments came up. Now, I'm a theoretician, so I can ask myself, was this a prediction of theory? Well, I would say yes, but surprisingly, it was not formulated as such by theoreticians. Theoreticians are often modest and say, well, it's not a strict prediction, it could be otherwise, but it would be very convenient if you had the following. If you had a three-factor rule modulated by reward or modulated by surprise. And this is really how theory works, this kind of conceptual theory. Over many years, over decades, these ideas go over from theoretical discussions into experimental discussions, and at some point the experimental tools are available and people can do the correct experiments that just prove or disprove one of these claims. With this, I'm at the end. This is not my work, this is the work of many people in the lab. I would like to mention in particular Johanni Brea and Vasiliki Liakoni and Alireza Motir-Shaneki. Then Marco did the psychophysics experiments and the analysis of these, its collaboration with Kirsten Broishoff, and the spiking network simulation was developed from scratch by Martin Burry, who is a PhD student in the lab. Thanks a lot for your attention, and I'm happy to take questions now.
Thank you very much. It was a brilliant talk. I think there is one question that has been typed in the chat. I will read it aloud. And given that these days we see a surge in the use of development of backpropagation-based learning methods, how does this compare when considering the examples based on Hebbian learning?
Yeah, great question. Of course, the whole field is now excited about these deep learning methods. All the work with deep learning is based on backprop. Backprop is fundamentally more powerful. Okay, so with backprop you can learn whatever you want. Well, that's not that's theoretically true. In practice, it's still correct to say that you can learn things well if the architecture is adapted. So a lot of prior knowledge goes in the architecture. Image recognition works well if you use a convolutional network, otherwise it doesn't, and this kind of stuff. But on a first level, backprop, these gradient-based optimization methods are just so much stronger. Now, these backprop methods need very specific feedback pathways. And personally, I don't believe that these feedback pathways exist. So with a specific feedback pathway, I mean that basically every synapse needs precise information whether this synapse should go up or down. That's one thing. And moreover, this information can be positive and negative and goes through many other neurons. So it's really a precise pathway through many other neurons that are closer to the output. I don't think that this exists. So if you just have Hebbian learning, which is what I started off, the two-factor rules, it's way too weak. You can explain receptive field developments in visual cortex V1, but that's it. Now with Heppian learning and little bit of competition, so this very classic competitive learning, you can actually extract place cells from fuse. So this is, you can just take snapshots of the environment and then bind them together, again with Heppian learning, and have something like place cells. But then this is still not able to do goal-directed learning. But then on this place cells that are made with Heppian learning, you can now use reward-based learning, and reward-based learning is a three-factor rule. It's Heppian combined with reward minus expected reward. So that was my first example. But these framework, okay. Now, so these three-factor rule with reward, they work if the state representation is already well done. It happens that place cells are great and you can do them with Heppian learning. Object recognition, sort of binding together all these different possible views and sides of an object, is not accessible to Heppian learning, and is also not accessible to the three-factor rules unless you do two more things. You go into a more hierarchical representation. You use surprise in that. But then you also have to have this kind of prediction that's part of now what I showed you in this spiking surprise. Then you can start to stack and get object representation type things without any backprop. But if you go for applications, you want to do data processing, please use backprop. Don't use this biological stuff. Yeah.
Thank you. Stefano Panzeri.
Hi, Wolfram. Can you hear me?
Yeah.
Very nice talk and very nice work. And I like both the models, but also the human psychophysics. And I have a question about this. Have you started thinking maybe with some collaborators about generalization of this kind of experiment that could be done by mice maybe, so that at some point you can also record the combination of activity in neuromodulatory nuclei and some other brain structures to kind of,
I think
this
that
stuff a bit closer at level neural computations.
Yeah, I think that is possible. I thought about this. So many of these I showed the psychophysics in the context of reward-based learning. That, of course, is done with mice, but I also showed my psychophysics collaborations in the context of surprise.
Yeah.
Now, surprise.
I meant about surprise.
Yeah, surprise is often done in the context of oddball tasks, auditory oddball tasks. And you can imagine the kind of experiments being that sort of the psychophysics I showed here being translated to more generalized auditory oddball tasks. The limitation of oddball tasks right now is normally it's done just with two stimuli. And then it's not clear whether it's just neuronal adaptation or synaptic depression or whether it's really high-level concepts, but that are linked to surprise. But you could sort of generalize this and build sort of like little melodies played to mice, and then you do little changes, but in a systematic fashion. So you have to get from 2 beeps of different frequency to 8 beeps, and then you can do exactly the kind of sequences I showed, show some regularity and build somewhere sort of a 50% chance to go somewhere else. And that's sort of one of the things I'm in discussion with a group in Switzerland where we could potentially do this.
Very nice.
I have a brief question. I was fascinated by the idea of the surprise in terms of biophysics as potentially the actor modulating or unbalancing excitatory inhibitory balance. But neuromodulators biophysically are also affecting cell excitability. Do you think that there is both action for this unbalancing of excitation inhibition that is happening both at the level of synaptic transmission and at the level of single cell transfer properties, or it's only synaptic?
Yeah, neuromodulators have many actions, as you say, and sort of the classic view that was prevalent for many decades was that first, neuromodulators are slow, and second, that they basically change excitability. And now modern work shows that the neuromodulators also have precise phasic signals, but it's still true that they affect excitability. So I focus, it's again a little bit like what I said, spanning a space and rotating a coordinate system. I'm not saying that this is the only thing they are doing. And we should get out of this framework that we classify cells by their receptive field properties and say, this is a visual cell and this is an auditory cell. And in the same way, we should get out of saying, this is this one thing is what a neuromodulator does. Yeah, neuromodulators do lots of things, but that basically relates back to the trend of deep learning now. Maybe we get more used to think in high-dimensional spaces. And if a population as a whole spans the correct space, then you can do lots of things in that. And yeah. So you just should think not always in terms of one-to-one mappings, but in terms of, okay, of my 5 modulators, they span a space. Moreover, but then how it's used by cells and synapses is sort of some cells look at one combination, others at that, and then the readout might come with different temporal filters. I know you think a lot in terms of temporal filtering properties, but it's exactly this. So I have these signals. Some cells will look at a high-pass filtered versions, other as a low-pass filtered version, and maybe one of these leads to excitability changes and the other to synaptic changes. I don't know. All of this is speculation.
Thank you. Any other question from the audience? If not, I have another very brief question to conclude. I read somewhere a few years ago that theories in neuroscience are scarce. How is your point of view? What do you think about the role of theory in neuroscience?
Yeah, so there's a difference between theory and, so say, model prediction. Yeah, so with a Hodgkin-Huxley type model, well established biophysics, everybody can generate 10 hypotheses per day, just sort of blocking some channel and saying down, this is what I see. So that's possible, but that's not what we mean by theory. So by theory, the way I understand your question, I would now understand conceptual theory. And conceptual theory is you try to format the thinking that how you look at phenomena, how you look at data. And I think that is very influential. So the successful theories like excitation inhibition balance and fluctuations arising out of that, it's a theory. It has influenced the way experiments are done now. Population coding instead of single cell receptive field coding is also a conceptual theory framework. And I would claim that this kind of, sort of the story of Wolfram Schultz and Peter Dayan about reward-related learning that really has influenced the field. So that's also conceptual theory. It's the theory of reinforcement learning that has influenced. So I think theory is something that exists and that is developed and that's very influential and very successful. And that's why I added this last slide, but sort of this kind of conceptual theory has an effect on a time scale of years or decades. And it's not on this please now generate 5 concrete predictions. because we know that this is one theory and there could be another one. We don't say it has to be like this, but it could be like this. And then, the attractor networks, Hopfield networks, associative memory network, also very successful theory. But sort of in 1982, when it came out, everybody said it's not biological because of this, because of that, and you can name it. So positive and negative rates, transfer function wrong, symmetric weights, 50% activity in each pattern. And then all of these obstacles were removed one by one. And at some point we realized it's just attractors. And then in around 2000, many experiments came out that show attractor dynamics. So yes. So again, that's an example of a theory. It exists. Theories exist. They are influential and influence the experimental field the way neuroscientists think, and that's the role.
Thank you. I think we are out of time now, and I would like to thank Professor Gerstner once more and all of you for attending this keynote session.
It was a pleasure to be here, and thanks for moderating this so successfully, Michele.
Well, at this stage, I would like to thank again Professor Gerstner, Professor Giuliano, and all other attendees for attending this session. And this brings us to the fourth keynote speech of this morning. And for that, I am requesting Professor Deshpande to kindly chair the session.
Thank you, Dr. Mahmood. Thanks a lot for inviting me to chair this session. And I have the pleasure of introducing Professor Tianzi Jiang. I'm sure most of you know him very well. I mean, he's a world leader in the field. He has a pretty long biography, but I would give a very brief introduction to Professor Jiang. He's the director of the Beijing Key Laboratory of Brainatome and director of the Brainatome Center at the Institute of Automation of the Chinese Academy of Sciences, and the chief professor of the University of the Chinese Academy of Sciences. He's also a Chang Jiang professor at the University of Electronic Science and Technology of China and professor at the Queensland Brain Institute in Australia. His research interests basically span neuroimaging, brainatome imaging genetics, and their clinical applications in brain disorders. So if you work in the area of neuroimaging, I'm pretty sure you have seen his papers and you're aware of his contribution. He's also the author and co-author of over 300 peer-reviewed journal papers in this field, with a total citation of more than 30,000 on Google Scholar and an H-index of 83. So his study on the human brainatome has been ranked as one of the main breakthroughs, both within China and abroad. And he's been an elected member of the Academy of Europe and a fellow of IEEE and IAPR, as well as AIMBE. So as you can see, he's achieved a lot, and he's also received numerous awards for this, including the Helmholtz Award, Wenjun AI Distinguishing Contribution Award, and as well as a Natural Science Award. So with that, let me have the pleasure of inviting Dr. Tianzi Jiang to deliver this keynote talk. Welcome.
Okay, I have a video.
Everybody, I'd like to thank the organizers for inviting me to deliver a keynote lecture on this conference. I will talk about how to tackle grand changes in brain health with artificial intelligence. My talk is divided into following 5 parts. I will first give a brief introduction on the challenge in brain health. Then, I will present a new brain atlas called the Brainatome Atlas. After that, I will present how to use Brainatome Atlas for diagnosis and therapy of brain disease. Finally, I will give a brief summary and perspectives. In this talk, I will focus on neuropsychiatry. I think there are 3 grand changes in neuropsychiatry. First, there is no any objective diagnosis in neuropsychiatry. Second, it is lack of individualized treatment for patients with mental disease. Third, it is also lack of precision therapy target for mental disease. In order to address this challenge, I think we need a fine-grained brain atlas, a big medical dataset, and also some proper artificial intelligence method. We can study the brain from a view of network. So the mental disease is a lot of abnormality, as Thomas Ince suggested. Here we show some example. Depression is a mood disorder. Image of brain region most developed in depression points to borderline area 25. It connects directed to structures such as the amygdala and the hypothalamus. These regions in turn exchange signals with the hippocampus and the insula. The second example is the obsessive compulsive disorder. The abnormal network consists of coded nuclei of the front cortex, thalamus, and so on. The third example is post-traumatic stress disorder. It was also found abnormal network with the HAPA and ventral medial prefrontal cortex. In this talk, we demonstrated how to find the neural image biomarker for brain disease from a view of Brainetum atlas. Will be presented in detail in what follow. There are more and more UK Biobank, the Human Charactome Project, and its follow-up projects ABCD for lifespan study, ADII for Alzheimer's disease, and so on. We also embarked on one project on the Brainetum of schizophrenia in 2010. In that project, we connected over 1,200 patients with schizophrenia and the health control, which include detailed multimodal MRI images, genome data, and clinical score. These brain imaging initiatives with a fine-grained brain atlas will provide excellent opportunity to address challenges in brain health. Now, I present the Brainetum atlas. In this part, I'll first talk about the definition of Brainetum. Then, I'll talk about how to construct the Brainetum atlas. After that, I'll present the validation of the Brainetum atlas. The Brainetum takes brain network as basic research unit, which consists of two components, node and the connection. The Brainetum can be studied on different scales, from neuron to brain region. The nodes and the connection of the Brainetum can be defined at different scales and levels. On the micro scale, the node and the connection are neurons and the synaptic connections. On the meso scale, the nodes and the connection are a set of neurons with similar features and the connection. On the macro scale, the nodes and the connection are brain regions, and the connection defined with diffusion mark, function mark, or other functional image. The Brainetum includes at least the following 5 themes. The first one is topological structure of brain network. The second one is the dynamic and characteristic of brain networks. The third one is network manifestation of function and malfunction of brain. The fourth is genetic basis of brain networks. And the fifth is simulating and modeling brain network on supercomputing facility. Now I'll talk about how to construct the Brainetum atlas. Brain atlas has a long history. It can track back to the most famous Brodmann atlas, launched in 1909, which was created with human brain architecture. Brodmann atlas is too rife because it possesses the cortex into 52 regions. The Ulrich Research Center has started to improve the Brodmann atlas since about 1996. the new brain atlas called the U-Brain Atlas, which also uses human brain structure architecture. This is a milestone of the Brain Atlas, but it has not completed yet. The Brain Atlas uses a completely different method from the Brain Atlas with structure architecture. Brain region has unique features that for each workers, we can define its connectivity profile with other workers of the brain image. We can define the anatomic connectivity profile with diffusion MRI and the functional connectivity profile with functional image. If two workers have the similar connectivity profile, they should be in the same brain region. Otherwise, they should belong to different brain regions. So we can partition the brain region into different subregions with connectivity profile. The Brain Atlas has been established with anatomical connectivity profile. The pipeline of the Brain Atlas are as follows. First, structure MRI is used to extract the target brain regions for passation. Then, the anatomical connectivity profile for each works are obtained with diffusion MRI. After that, we can obtain the similar matrix between seed region and other region of the brain. Finally, we can distinguish the subregion with a cluster algorithm and map back to the brain and finish the brain region passation. Here we demonstrate how to create Brain Atlas with two types of brain regions. One is the brain region with heterogeneous structure architecture, such as posterior medial cortex. This region can be partitioned into different subregions with structure architecture. With the anatomical connectivity profile, we can also partition it into 5 different subregions. Moreover, we can provide the connectivity profile for each subregion. This connectivity profile are similar to connectivity profile of monkey brain obtained with track tracing. Another type is the brain region with homogeneous structure architecture, such as temporal pole. It is impossible to partition this kind of brain regions into different subregions with structure architecture. However, we can partition the temporal pole into 3 different subregions with anatomical connectivity profile. We can also obtain both anatomical and functional connectivity profile for these 3 subregions. It has taken 7 years for us to complete the human brain atlas. It includes 210 brain images for cortex and 36 regions for subcortex. The Brain Atlas provides a fine-grained, cross-validated atlas and contains information on both anatomical and functional connections. It has been attracted more and more attention and has been applied in brain science and brain disease. In what follows, some examples will be shown. The Brain Atlas not only provides a brain atlas, but also provides a number of software and resources for network analysis and visualization. Please contact with me if you have any question during use this atlas. The Brain Atlas was recommended in platform and popular software. For example, it is available on Neuroinformatics platform of Human Brain Project. It is also available in popular software such as SPM. Now, I will discuss why the Brain Atlas is reliable. First, I'd like to demonstrate that the methodology of Brain Atlas is reasonable. Then, I show the Brain Atlas is reliable with cross-modality comparison. After that, I present the genetic basis of Brain Atlas. The brain can be partitioned into different brain regions with various brain information, such as structure architecture and connectivity profile. We have demonstrated how to establish Brain Atlas with anatomical connectivity profile. This is because the connectivity plays a fundamental role in making brain areas distinct. Why anatomical connectivity profile are good choice for Burnett atlas? This is because anatomical connectivity profile can predict the brain function. One study demonstrated that anatomical connectivity profile can predict face selection in the fused form gyras. It remains unknown if anatomical connectivity profile can predict other functions. Here we address the following two questions. The first one is whether anatomical connectivity profile can predict the functional activation across different cognitive domains. If the answer to this question is yes, the second question is whether there is regional difference in the connectivity function relationship across the full cortex. Here, we use 7 tasks from Human Connectome project to address the first question. We show that anatomical connectivity profile can predict the functional activation across different cognitive domains. The left part of figure is the predicted activation of 7 tasks. The right is actual activation of 7 tasks. The table on the left side shows that the accuracy of prediction is very good. So the answer to the first question is yes. Since the anatomical connectivity profile can predict the functional activation across different cognitive domains, we can define the connectivity functional relationship by predicting activity from anatomical connectivity profile across cortex. Then the second question can cast as whether there is a region difference in the connectivity functional relationship across full cortex. We first classify the brain regions of cortex into 7 functional networks, that is, visual and motor auditory network that constitute the sensory motor network and the dorsal and ventral attention, limbic, frontoparietal control, and default motor network that constitute the association network. The color represents the mapping of 7 networks. Then, spatial distribution of connectivity function relationship and the rank of connectivity functional relationship in 7 networks are shown in different subplots. It demonstrated a hierarchy of connectivity function relationship across full cortex from sensory motor network to association network. Moreover, the hierarchy of connectivity functional relationship was correlated with the hierarchy of mining, functional flexibility, and function variability. Now, I'll show the second way to validate the Burnett atlas with cross-modality comparison. The postulation with static architecture is a traditional method on micro scale. We first make a comparison of Burnett atlas with U-Brain atlas, which was created with static architecture. There are a large number of studies demonstrated that the topography of postulation based on connectivity profile is consistent with postulation based on static architecture. For example, the top left figure is the postulation of human Broca area. The top right figure is the postulation of human left inferior parietal lobule. The bottom left figure is the postulation of the human superior parietal lobule. The bottom right figure is the postulation of human nuclear accumbens. The first 3 regions are in cortex, the last one in subcortex. Every region can be postulated with different types of connectivity profile, such as anatomical and functional connectivity. Here I show 2 examples. The left figure shows that superior parietal lobes pasteurization result use diffusion MI, functional MI, and co-activation method. It demonstrated that the topologicals of pasteurization are highly consistent. The right figure shows that the left dorsal premotor pasteurization result with multimodal imaging. It is a long-standing question, where is the boundary of vertical areas? We take a region. All research thought it is vertical areas as a city region. Then we use atomic connectivity profile to pasteurize this region into 3 subregions. We use intraoperative electronic stimulation to confirm that only anterior and mid parts are related to language. The posterior parts is not related to language. This validates the posterior boundary of the vertical areas. We also pasteurize the nuclear accumbens into 2 different subregions called shell-like and core-like subregions with diffusion MI, functional MI, and co-activation method. The topographies of pasteurizations with 3 methods are highly consistent. It was consistent with earlier architecture studies on shell core organization. In this part, I'd like to show the genetic basis of brain pasteurization with anatomical connectivity profiles. In the last section, I have demonstrated that various brain structure and functional features such as structure architecture, tomography mapping, Jara and Saka, anatomy, and anatomic and functional connectivity has been used in human brain pasteurization. The result of pasteurization based on various phenotypic features are consistent for some regions. Take the Broca iris as an example. This is a pasteurization based on receptor distributions. The bottom figure shows the pasteurization based on connectivity profile. We can see the topography of 2 pasteurization schemes are consistent. That means cortical regionalization may be influenced by underlying genetic mechanism. Animal data demonstrated that the development of cortical areas is controlled by interplay of intrinsic and extrinsic mechanism. In the early brain, differential gene expressions plays an important role in the process of cortical patterning. So animal studies have shown that region-specific genetic influences are responsible for cortical patterning. It is unknown if equivalent mechanism governs the patterning of human brain. 2 studies review a coarse genetic organization of cortical surface. They found 4 genetic divisions are consistent with mouse brain regions. 12 genetic divisions correspond to meaningful structure and function regions. Genes also influence the cortical patterning in subregions such as frontal cortex. However, it is unknown if genetic information can feasibly be used to identify fine-grained cortical subregions and reveal the genetic basis of cortical regionalization. Now, I'll summarize the genetic correlation-based pasteurization pipeline. First, use T1 vertical image data from human twins to explore detailed genetic pattern of seed regions. Second, the cortical surface area for each vertex in cortical surface was calculated. Each hemisphere was downsampled from a large number of vertices. The left supramiddle frontal cortex was used as an example of seed regions. Third, biovariable AE models were used to estimate the pairwise genetic correlation between the surface area of vertices within the seed region. Fourth, generate a square genetic correlation matrix use all twins data. Fifth, spectral clustering was applied to the genetic correlation matrix. generated the population result for city regions. Finally, estimated the genetic correlation of morphology based on the twin stretches, built a fine-grained genetic architecture. Here I show some regions where postulated with genetic correlation. The top left figure shows the postulation of superior medial front cortex. The top right figure shows the postulation of front paw. The bottom left figure shows the postulation of inferior front gyrus. The bottom right figure shows the postulation of primary motor cortex called M1. M1 was able to be reproducibly subdivided into 6 subregions. 5 of them corresponded to motor representation of face, hand and arm, trunk, hip, leg, and figure. These examples demonstrated the postulation of brain regions with genetic correlation are consistent with the result obtained with connectivity profile and other method. Moreover, it was demonstrated that the genetic correlation similarity matrix correlates with the functional connectivity similarity matrices. So, the genetic correlation determines the cortical pattern, which validates the genetic basis of Brain-Anatomy Atlas. Now, I move to the application of Brain-Anatomy Atlas and artificial intelligence. In this part, I'd like to present the study on application of Brain-Anatomy Atlas in diagnosis and prognosis of disease. In the first study, I show how to use the Brain-Anatomy Atlas for finding the neuroimage biomarker in schizophrenia. The second study is the application of Brain-Anatomy Atlas in exploring neuroimage biomarker for sustained experimental and clinical pain. The third one is the application of Brain-Anatomy and artificial intelligence for prognosis of disorders of consciousness. As I mentioned in the first section, there are 3 grand challenges in neuropsychiatry: non-objective diagnosis measurement, non-individualized treatment, and non-precision therapy target for mental disease. More and more attention is attracted to these issues. We have embarked on one project on this theme 20 years ago. Here, I show one study on schizophrenia. To establish a clinical use for resting state functional biomarkers, we need to achieve the following major goals. First, obtain reliable individualized measurements. Second, achieve reproducibility and generalizability across independent populations and sites. Third, achieve the biological interpretability and mechanistic plausibility. Here presented the methodology and the main result in this study. Figure A shows that we use Brain-Anatomy Atlas to extract the stratum. Then, 3 distinct in vivo straight image markers were included to systematically characterize the straight function. They are region singular, intrastratum, and extrastratum functional connectivity, which are called the functional strata abnormality. Figure B shows that statistical analysis was performed for data acquired across multiple MR scanners and demonstrated reproducible functional strata abnormality patterns. Figure C shows that a machine learning model found generalizable predictive patterns of functional strata abnormality and use them to predict eye-observed diagnosis status in independent population. Figure D shows that the individualized functional strata abnormality score predicts the diversity of short-term antipsychotic response in independent populations. Figures show that special patterns of elevated striatal spontaneous brain activity where investigators use complementary analysis of molecular imaging and transcriptomic data. They revealed that a significant special association between striatal dopaminergic function and the expression profile of schizophrenia risk gene. With the Burnett Atlas, machine learning method, and the bigger clinical data, we developed a new hypothesis-driven neural image biomarker for schizophrenia based on functional striatal abnormality. We also established the utility of this biomarker in predicting antipsychotic treatment response, clinical stratification, and elucidate striatal dysfunction in neuropsychiatric disorder. Now I present a study on neural image biomarker for sustained experimental and clinical pain with Burnett Atlas. Pain is a major clinical and social problem and is difficult to access objectively. Long previous human neural image studies have directly examined how the neural representation are similar or distinct among the tonical experience pain, physical experience pain, and clinical pain. This study addresses the following question. The first question is, can we identify brain markers of tonic pain based on the full brain functional connectivity? The second question is, can the tonic pain mark serve as a model explaining clinical pain severity? The third question is, how similar or distinct are the functional connectivity model among tonic pain, clinical pain, and experienced physical pain? This study adopted 4 brain populations for modeling training. They are Barclay's population, Burnett Atlas, Connectome Project multimodal population, and the Oasis population. Total of 5,916 candidate models were generated for each outcome variable. According to the composite score, with predefined 7 criteria, a model constructed based on the Burnett Atlas is selected as the best model across all 5,916 candidate models. This also shows the tonic pain signature as a functional connectivity marker for tonic pain. Figure shows the low predicted weights of the model. The brain regions were sorted according to the functional network membership among the 9 functional networks. Figure B shows the network level representation of tonic pain signature. Figure C shows anatomical region level representation of tonic pain signature. This study developed a functional connectivity-based signature for tonic pain with potential for clinical application. Tonic and clinical pain showed a similar network level representation, particularly in somatomotor, frontoparietal, and dorsal attention network. These patterns were distinct from representation of experimental physical pain. It demonstrated that the Burnett Atlas has the best population among 4 counterparts. Here I present an application of Burnett Atlas and artificial intelligence in prognosis of disorders of consciousness. Severe brain injury leads to disorders of consciousness. The prognosis for a patient with disorders of consciousness is based on physical observation of the patient's behavior. In this study, a prognosis model was proposed by combining the resting state function of MRI with etiology, age, and duration to predict 1-year outcome at the individual patient level. We propose a hybrid prognostic model that combines the resting function MRI with 3 clinical characteristics, including age, duration of disorders of consciousness, and etiology. Based on the regression formula, we noted some interesting findings. First, there were both positive and negative weights. In particular, the weights were all positive for 3 brain area connection feature, whereas the weight for the functional connectivity feature between the anterior middle prefrontal cortex in the default mode network and the dorsal middle prefrontal cortex in the executive control network was negative. Interesting. This connection has maximum SMC F value as shown in figure B. In addition, the edge and the alloxy etiology has negative weights, and the edge predictor has the largest SMC F value among the 4 clinical features. Here I show the performance of prediction model on the training datasets of 63 disorders of consciousness patients. The prediction accuracy was 92%, sensitivity is 85%, and the specificity is 94%. The performance of prediction model on 2 testing datasets is illustrated in this figure. We found that for the Beijing data, the prediction accuracy was up to 88%, while for the Guangzhou dataset, it is also up to 88%. More interesting, for the tested dataset in Beijing, 8 disorders of consciousness patients who were initially diagnosed as vegetable state subsequently recovered consciousness. Using the proposed model, we could successfully identify 7 of these, and there was only 1 false positive case. Using statistical analysis, we found that the predicted accuracy of combinational model was statistically superior to the ones use the clinical features alone or use the image features alone. To our knowledge, this is the first implementation reported of the multi-domain prognostic model based on the resting state function and the clinical characteristics in chronic disorders of consciousness. In this study, we introduced a prognostic model that combines the resting state function with clinical characteristics to predict 1-year outcome at the single subject level. The model discriminates between patients who would let recover consciousness and those who would not, with the accuracy up to 88% on 3 datasets from 2 medical centers. It was also able to identify the prognostic importance of different predictors, including brain function and clinical characteristics. Now, I move to application of Brunet models in therapy of brain disease. In this part, I take Parkinson's disease as an example. A lot of studies show that deep brain stimulation was superior to the best medical therapy in the treatment of Parkinson's disease and improve impairment and disability. However, it was found a number of limitations for deep brain stimulation in Parkinson's disease therapy. 30% cases have no response or with side effects, 20% without cognitive function, 30 times higher suicide rates, post-operative depression significantly associated with attempted or completed suicide. From a view of Brunet models, the above limitation can be understood clearly. For DBS therapy in Parkinson's disease, the target brain region is subthalamus nucleus, which can be divided into 3 subregions. One is related to motor, other 2 subregions are related to emotion and social cognition. If the stimulated electrode is put in the motor-related subregion, the treatment outcome should be satisfactory. However, if the stimulating electrode is put in other subregions of subthalamus nucleus, it may cause some side effects mentioned before. We proposed Platinum Atlas guided neuromodulation robotic system. The Platinum Atlas is a powerful tool for therapy targeted localization. Neuromodulation robotic system can realize the robust and accurate implant of the stimulate electrode. This is a diagram of the Platinum Atlas guided neuromodulation robotic system. It includes 3 core modules: treatment planning system, positioning and navigation system, and a robotic arm with end of effectors. It is also includes live feature monitor device, live feature dynamic monitor system, and a central software and hardware control system. Transcranial magnetic stimulation, called TMS, is a invasive therapy equipment which is widely applied in the brain disease and cognitive science. We have successfully developed the first type of Platinum Atlas guided neuromodulation robotic system for TMS. Other types of Platinum Atlas guided neuromodulation robotic system for DBS and other therapy method and development. This is a very promising field. It envisions to play an essential role in the treatment of brain disease. Finally, I will give a summary of this lecture and some perspectives for future research in this field. A number of challenges in brain health and potential solutions were present in this lecture. Then, I present a fine-grained brain atlas called the Platinum Atlas, which was created with anatomical connectivity profile. I also present 3 ways to validate the reliability of the Platinum Atlas. After that, it was demonstrated that the Platinum Atlas plays an essential role in diagnosis and therapy of the brain disease. In this lecture, I give a detailed presentation on Platinum Atlas and its reliability from different aspects. It was created with adult datasets aged 20 to 29. This population have stable development. The Platinum Atlas offers a new avenue in the interdisciplinary field of the brain science and brain disease. We can summarize the future research directions as one body and 2 wings. One body means the study of Platinum Atlas itself. 2 wings means 2 application fields. One wing is Platinum Atlas-based paradise for diagnosis and therapy of brain disease. Another wing is Platinum Atlas-based brain-inspired computing. Regarding the studies of Platinum Atlas itself, a lot of questions need to be addressed. First, how development and aging influence on the topography and connectivity profiles of the Platinum Atlas. Second, what is the evolutionary mechanism of the Platinum Atlas? It is impossible to study what makes us human from a view of Platinum Atlas across species. Third, how to integrate genome, protein, and other multimodal images datasets in the Platinum to create a complete landscape of the brain. Multi-scale mountain Platinum Atlas is an emerging frontier of science and translational medicine. The methodology of human Platinum Atlas on microscale can be extended directly to macaque monkey, which is a human close relative Besides, we can create the massive scale connectivity atlas of monkey brain with various image technology. For example, the structural connectivity atlas of the monkey brain on massive scale can be created with PSOCD, trace imaging, large-sheet microscope, and so on. The functional connectivity atlas of the monkey brain on massive scale can be created with two-photo image, photoacoustic imaging, microaeroscopy, optogenetics, and so on. What makes us human? This is a big challenge and infinite frontier for multiple fields. We can address this question from following directions. We can make a comparison of the genome between human and non-human primates to find out what genes are unique for human. We can make a comparison of multi-scale Burnett atlas between human and non-human primates to find out what is different between them. We can also make comparison of the cognition and behavior between human and non-human primates. A lot of studies show that the language and tool use are human-specific compatibility. In what follows, I will present one Burnett study related to about two capabilities. Language is the only behavior that is universally accepted unique for human. A striking feature of language is lateralization, usually lateralized to the left hemisphere, and is involving inferior parietal lobes called IPL. Complex tool use is a large human-specific behavior, which is also show lateralization and involves IPL. Recent evidence suggests that the IPL show asymmetry in cortical folding, cortical thickness, and surface area. But how and whether this asymmetry evolved from other species remain unknown. In addition, whether the different structural asymmetry pattern in the subregions of IPL is present in other species remain unknown. We first divided the IPL into 4 subregions using methodology of Burnett atlas with 40 human subjects, 27 chimpanzee subjects, and 8 macaque monkeys. We then extracted the volume of each subregions and calculate the asymmetry. Chimpanzee and the human show a similar dichotomous asymmetry pattern in the IPL subregions, that is, left-forward asymmetry in the anterior parts and the right-ward asymmetry in the posterior parts. But macaque did not show any asymmetry. These results provide evidence that the local structure asymmetry of the IPL is present in chimpanzee, but not the unique features of human. Therefore, we assume that another feature, the connectivity, may be important to the human-specific function. A vertex-wise statistical analysis was performed on connectivity profile of each subregions for each species. For each subregion, the higher order the primate, the more connectivity asymmetries. In addition, the regions show connectional asymmetry was related to handedness, language, and tool use. These results suggested that the evolution of asymmetrical pathway from the inferior parietal lobe that is already present in chimpanzee and to its great extent in humans, which might be related to the evolution of language in humans. In this study, 4 subregions were identified in IPL across species, A similar asymmetric pattern was found in chimpanzee and human IPL subregions, but long asymmetries was found in macaque monkey. Moreover, connectional asymmetries of the IPL in human, chimpanzee, and macaque show a gradient pattern. It may support the neural pathway evolution that might be related to evolution of language and to use in humans. This study provides an example for us to address the questions, what makes us humans? Thanks to my colleagues and students at the Institute of Automation, the Chinese Academy of Science, I also thank my colleagues and students at the University of Electronic Science and Technology of China. Thanks to Professor Chun Shui Yu at Tianjin Medical University. Thanks to Kanjuan Mats, Simon Akfov, and Sylvania Kaspers at the URIS Research Center. Most of the staff present in this lecture is from my lab. It was supported by a lot of grants from Chinese government, such as National Natural Science Foundation of China, the Ministry of Science and Technology of China, and the Chinese Academy of Science, and so on. Finally, I'd like to thank you for your attention.
Well, Professor Jiang, thank you so much for that very interesting talk. We do have about 10 minutes for questions. I would start off with a question that was typed in the chat box by Professor Miyapuram from IIT Gandhinagar. The question is, how is meta-analytic co-activation included in constructing the atlas? Would be interesting if you could elaborate.
Okay, so in fact, we really use the co-activation method. So first we use this kind of method to evaluate the postulation. As you know, we use the connectivity profile to postulate the brain. So then we can also use the co-activation to postulate the same regions to compare what is different, what is the same. So the second, we can also use co-activation to find each sub-regions, how to connectivity with other parts of brain. So then based on this kind of things, we can decode each sub-regions. So what kind of function is related? So this is my response to this question. So that's okay?
Yeah, thank you.
Good. So if you're interested, maybe you can also welcome, maybe we can discuss in detail. So each sub-regions, in fact, in our Atlas, we give a very detailed preliminary results. So especially for behavior analysis.
Any other questions, audience? Okay, while the audience ponders about the questions, I have a couple of questions. So in your introductory slide, you mentioned something about computational complexity, that you're using supercomputers to do some of the computations. So I'm just wondering which part of the pipeline is most computationally complex that would actually be helpful to use something like a supercomputer?
So in fact, in our labs, we just use the popular CPU or this kind of things to construct a group computer. So, but we can also use some supercomputer, for example, in China, this kind of is very high performance. So this depends. So we just got a new project, just focus on Bulletman Atlas, especially for modeling and analysis. So this for this kind of purpose, we did a very high performance computer facility.
Okay. Another question I had was, so how is this postulation dependent on gender and race? mean, you mentioned that you have taken the age range of 20 to 29 when basically the brain is very stable. And that is perfectly, that's a perfect logic. But I'm assuming that the postulations might be different across males and females and also across different ethnicities.
So this is a good question. In fact, we also consider the sex difference. So for example, male and female, but on this kind of, so resolution. So this is a big difference between male and female. So we also compare the different, maybe some people from China, some people maybe Caucasia, or this kind of things. So we also can get the same result. So I think if you want to find some difference, maybe you should focus on some specific regions. For example, some region may be related to language or to some specific language or this kind of things. Maybe we can find some things which is very different. So, but so far we have a lot to do this kind of things. So another important things, in fact, aging and development should affect the brain matter loss. So recently we have a new study that's to compare to age 8, 10, 12, 15 to 8, so different aging. So in fact, especially from the aging 18, so this will, some regions become 2, so 1 become 2. So this is very interesting. So how aging affects the brain matter loss? So we have a lot of studies, this kind of study. I think it should you find some interesting things.
Okay. Any other questions from the audience? Okay. The final question I had was, I saw your wonderful paper in eLife comparing the chimps, macaque, and the humans.
Yeah.
Have you done any other cross-species studies? Because we work with dogs. I mean, it would be really interesting to see how dog brains and human brains differ from monkey brains, especially given the social capabilities of dogs.
So in fact, this is just a very preliminary study. So we choose the inferior parietal cortex lobe, because this is related to the tool use and language. So we expected they should have a difference between, especially chimpanzee and monkey and human. So, but we're very lucky. We really find some things, especially asymmetry. It's just some kind of this kind of things. So in future, we will do have very sophisticated studies. So so I mean, so across species studies, especially in primates, human, monkey, especially not just focus on imaging, maybe also electronic physiology or some other method.
Yeah, okay. Let us chat offline regarding that. I'll send you an email. Okay. If there are no further questions, I think I would like to thank Professor Jiang for this very interesting talk. Thank you again for your contribution to the conference.
Okay, thank you all for your attention. Good.
Thank you, Professor
Thank you.
Jiang.
Bye-bye.
Thank you.
Thank you for your time. Before going for a lunch break, I would like to inform you that we have some exciting workshop today from 2 p.m. So these are actually international workshop on application and AI-driven tools towards inclusive and personalized education for students with learning disabilities, and also workshop on cutting-edge technology for human-computer interaction. Second international workshop on computational neuroaesthetics. International workshop on computational intelligence in healthcare. International workshop on internet adoption and mental health. A special session on imaging the young minds. A special session on new method and technology in brain imaging. So I would like to request all of you to join us at 2 p.m. for this exciting the workshop and a special session. Definitely, we will learn from our peers. So please tune. So this is a lunch break. So we will start at 2 p.m. UK time. Professor Zong, are you here?
Okay.
Would you like to add something?
Just thank you very much. Excellent keynote speakers, also the chairs. Thank you for great work. Okay,
So
we continue.
PM.
This afternoon, this workshop session. Also, please enjoy. Okay, thank you.
অলরেডি এই যে কিছুক্ষণ আগে কথা হলো ইক্যাবের মহাসচিব আব্দুল ওয়াহিদ কমাল ওনাকে আমরা একটা ইন্ডাস্ট্রিয়াল এক্সিবিশন করতে একটা সেমিনার করতে চাচ্ছি এটার জন্য ওই গেস্ট উপস্থিত হয় ইক্যাবের প্রেসিডেন্ট শ্রমিক আইসা তো শ্রমিক আইসারকে আমি সরাসরি ফোন দিতে পারতাম যদি মানা করে দেয় এই জন্য আমি আর কি করিনি আমি মহাসচিব উনি বললো যে ওনার শুক্রবারের দিন আমরা 24 তারিখ সাতাশ সাল বলতেছে 24 তারিখে করি আচ্ছা ঠিক আছে আমি দেখি
না বৃহস্পতিবার উনি বিজি
হ্যাঁ
বৃহস্পতিবার উনি বিজি
কে শাহাদাত স্যার
শাহাদাত স্যার
হ্যাঁ হ্যাঁ ওই জন্য তো না হলে একটু পিছাবো সমস্যা
আর ওই যে 22 তারিখের যে প্রোগ্রামটা বুধবারে
হ্যাঁ 22 তারিখ
ওইটা কনফার্ম আর কি ওটা সাজ্জাদ স্যার কনফার্ম করছে আমার মনে হয় ইমেল আমারই পাঠাইতে হবে ইয়ারের উপর ভরসা পাই না
see our
Hello, David.
Hi, Mufti, how are you doing?
I'm good, thank you. How are you?
Carl's having trouble getting in, Mufti.
Yeah. Usually should not be the case, but
I just asked him if he did use the link yesterday.
yeah. So shall I forward the link again to him?
Yeah. Yes, please, via email.
Okay,
Yeah,
okay. So I'll just forward the email again. Yeah.
yeah, thank you.
You're welcome.
Hello, David. How are you?
Hi, Shaman, how are you doing?
I'm fine, thank you.
Super, good.
So anytime I think Arif also will join, and there is Nadia, and Nadia's
Yeah.
student that was right.
Yeah, Nadia's student.
Okay.
I'll just try to share my screen as well.
Just a second that I will have to make. I'll make you co-host. Okay. So
Okay, all right.
there is some Zoom host joining, so I don't know.
Yeah, okay.
Okay, you are now co-host.
I'll try. I think Carl's in now. You there, Carl?
Yes, I'm in.
Oh, excellent. I was just about to send you an email, Carl, with the link again.
Yes, I got obviously the first link that was sent, and then I tried the second one. Everything worked fine.
Okay, I can see your screen, David. That's absolutely okay. There were some excellent keynotes since morning.
Excellent. Yeah. I'll have a look later on.
So there is also the YouTube link that I will forward to you.
Yeah.
So,
excellent.
Yeah. During a discussion, there was a discussion regarding how autism is connected to the basic brain network dysfunction.
Yeah, brilliant. I'll catch up with all the recordings. Looks great. I'm not sure if Nadia is going to be slightly late.
That's okay. Well, I think that we can probably wait a little bit for her to join.
Okay.
Shamim and Arif, we had some cool brain informatics backdrop.
Yeah.
For some reason, actually, it's playing with me.
Okay.
I tried it, but it's
It is actually PNG file. So
Yeah, it is the PNG file, yeah.
But it should be JPEG file, I think.
No,
Not
I'm using
40.
the PNG.
Okay.
I am using the PNG.
maybe I don't know actually.
Arif, try, it's working.
Yeah, I changed my background, but you see now become a hollow man.
Nice.
You can see that. Like,
yeah.
That's why I was not using that.
No, because I think the light is from your back. That's why.
Maybe. Let me try it. I don't know.
No, I think it is due to the background, because the background is somewhat.
Yeah.
I think it is because of the background, Arif.
Okay, let's skip it. That's not a problem.
Yeah. Well, you can
Hello,
get rid of
Tanya,
that.
how are you?
Oh, Alex is here as well. Fantastic.
Mufti?
Alex is here as well. Hello, Alex.
Hi guys.
How are you?
I'm very good actually. Yeah, I'm doing very well. Yeah, looking forward to this session actually. It looks really good.
Thank you.
All right then, shall we go?
Nadia will join us shortly. I think she was just going to grab a coffee.
Nadia is here.
Nadia is here.
Nadia
Yeah,
is here.
she is
Okay.
here.
Fantastic.
Okay, everybody. Well, welcome to the international workshop on the application of AI-driven tools towards inclusive and personalized education for students with autism, but also learning disabilities. What is the purpose of the workshop? We're holding a panel discussion today on the opportunities and challenges afforded by the use of AI and machine learning to support students with autism. This is in the context of our recently funded EU Erasmus AI Top project, which seeks to understand how AI can be used to predict when students with autism might have rumble moments, the precursors to a full meltdown. If we can predict when these students have a rumble moment, we can introduce evidence-based calming interventions to stave off the frequency and the intensity of meltdown events. The panel today, it sounds like gardener's question time. The panel today is formed of computer scientists, psychologists, and other people working in our project. So really getting together people working on the technical side of the project, but also psychologists and people who are experts in working directly with people with autism. Now, I think at this point, can we just go around the panel just to introduce themselves briefly, just to say hello and to say who you are, so that the other audience members will understand who's on the panel. And I'll start. I'm David Brown. I'm project leader and coordinator in computer science at Nottingham Trent, project coordinator for the AI project. Mufti, do you want to go next?
Okay, so I am Mufti Mahmood. I am working with David as a co-investigator in this project. So I have been mainly working at the interface of data acquisition and analysis. So applying different data analysis techniques, including machine learning and artificial intelligence, in trying to detect, let's say, rumble moment or specific moments when the autistic children show behaviors which are somewhat difficult to otherwise handle. So like the one that we call to be rumble moments, okay? So or the pre-meltdown state. And also we have worked a little bit on developing different methodologies for managing these students by analyzing their physiological or sensor-based data which are acquired from the environment as well.
Thank you, Mufti. Can we go to Shamin next, please?
Hello, everyone. This is Shamim Kaiser from Bangladesh. And
welcome, Shamin, to the project.
Yeah.
Well, Shamin, you're an expert as well in machine learning and AI.
Yeah. We are also working in with machine learning and AI for personalized learning for the student having autism.
Thank you, Shamin. Carl, can you go next before I introduce the opposition?
Good morning, good afternoon, or good evening, because I think you're all in different time zones. So my name is Karel van Isaker. I'm from Phoenix Care. We're a Belgium-based company, and we have been working extensively in the area of inclusive education. In the past, I think almost 20 years, something like that, with the team of Professor David Brown as well. So we are also involved in a top project. So that's it on my behalf.
Thank you, Carl. So as you might imagine, there are people working the project, psychologists, computer scientists, and technical people. I'd like to now introduce the members of the panel who are the psychologists, who are Nadia, Alex, and Nikki. So would you like to just introduce yourselves, and then perhaps Nadia, you go first?
Sure, thank you, David. My name is Nadia Haim. I am a senior lecturer in psychology at Nottingham Trent University in the UK. My main expertise is in individual differences in emotion processing and atypical processing, for example. So a part of this, I also look at autistic traits, but also other traits that may mean that individuals might struggle in general life, but also in educational contexts. And I'm on this panel here to inform more kind of probably from psychological theory in terms of my background knowledge of mental health and so forth. Thank you.
Thank you, Nadia. Excellent. Alex, would you like to go next? Sure. I think Alex is coming in from Croatia here.
I am, yes. So I'm Associate Professor in Psychology at NTU, Nottingham Trent University. And my expertise is really in the biology of how the body and brain work together and what happens physiologically when people move towards rumble moment, a breakdown, etc. And we've done a little bit of work around applying AI methods, neuroinformatics, to physiological measures like electroencephalographic activity, magnetic resonance imaging, etc., but also some very basic physiological markers like heart rate, skin conductance, etc. And so I've been involved in a few studies applying spiking neural networks to this kind of data to classify and predict different psychological states.
Thank you, Alex. That's incredibly interesting. Nikki, are you there today as well?
Hello, yes, I'm Nikki Stevenson. So I'm Nadia's student. I've just completed my master's. So I had to look at different neurological traits, including autism, in a domestic violence and abuse cohort. In my everyday life, I write and deliver autism training. So I'm currently delivering and have co-written the government's mandatory autism training It's called Oliver McGowan. So if you want to Google it and find out a bit more about it, you can. It's all over the internet. Thank you.
Excellent, Nikki, and welcome. So first of all, I just want to cover a little bit about our project, the context of what we're talking about today. We know that more than 1.1% of the UK population may fall within the autistic spectrum. In a focus study on 8-year-old children, 3.8 per thousand boys and 0.8 per thousand girls present with autism. Obviously, this is a huge issue, and the UK government started to develop their strategy in 2010 as Fulfilling and Rewarding Lives, and updated the strategy in 2014 as the Think Autism strategy. It had 3 main areas of focus: building autism-aware communities, promoting innovation in service provision, and providing integrated care. And really, we're really interested in promoting innovation in service provision with the use of AI to infer rumble moments. So it's important to provide students with autism with an environment adjusted to their needs, but also free of emotional trauma. There's a lot of research around autism in mainstream education. We know that about 71% of students in the UK attend mainstream schools if they have autism. But what teachers are saying is that mainstream schools are frequently neither fully educated or equipped to deal with the needs of an autistic child and give them the necessary support. And this means a large number of autistic children are not getting the educational experience they deserve. And additionally, the Autism Education Trust has shown that 40% of children on the autistic spectrum have been bullied, and 56% of parents whose children with autism have been bullied said it caused their child to miss school or even change schools, which means thousands of autistic children are being illegally excluded from schools. And Ambitious About Autism have researched this situation as well, and come up with the fact that 4 in 10 children have been informally excluded from schools, at least temporarily. This causes them to miss school trips, to miss activities, or even to attend lessons on a part-time basis. And it's not just teachers who think this is an issue. The National Autistic Society have said that 30% of parents themselves feel their child's educational placement is not adequate. And a staggering 70% of parents are not satisfied with the level of understanding of autism in their child's school. So really concentrating on our research in Nottingham Trent and our research in the AI Top project to understand that the environment should be adjusted to the needs of students with autism and free of emotional trauma. So very briefly, how do we do that? Well, we know that autistic children show some signs of distress before a meltdown event. And as Mufti said before, this is often termed the rumble stage. And cues, involuntary cues, the stage include rocking, biting, scratching, kicking, banging heads, or even lashing out violently. We can use these involuntary gestures, these behaviors, as a predictor of meltdown. We're using deep learning approaches to understand when a meltdown event might happen before it happens, and introduce evidence-based calming interventions. If we can do this, this will lead to a classroom or an educational environment which is more freer of emotional trauma. And for the students themselves, they might have less severe or less frequent meltdown events. So how do we do this? Very briefly, we know that the most important gestures that we could use to train machine learning classifiers are covering ears, covering face, biting hands, and flapping hands. So teachers and parents who are familiar with the students annotate video recordings of them approaching meltdown events, but also perhaps doing facial gestures which are not indicative of a rumble event. And we use those labeled, annotated images to train the machine learning classifiers. Now, research at Nottingham Trent has shown, because I always said it should be teachers, but there's lots of researchers, a few researchers in education, Lauren Dorg, who has really challenged my thinking here and said it actually should be the parents or the carers who should be annotating the video recordings because they know the students with autism best. And if we get very accurate labeled examples and feed those to the machine learning classifier, you're going to get a much more reliably accurate algorithm. The kind of machine learning approaches that we're using include deep recurrent convolutional neural networks to infer emotions. So what do we do? At the moment, in one of our projects, we have like a traffic light system. Green, calm, amber, approaching rumble, red in a full meltdown. So if we get probable examples of video images of students approaching meltdown, and we feed them to appropriate machine learning classifiers. We do this for enough students over enough ranges of context in different countries. We get very accurate machine learning classifiers that can really predict a meltdown event before it really happens at the rumble stage. What would be the outcome of that? We hopefully will have a learning environment which is freer, more free of emotional trauma. There will be a decrease in incidence of challenging behavior, leading to, for the individual student, improved mental well-being, and globally decreasing instances of absenteeism and bullying. And also for the students themselves, this can help prevent the secondary consequences of their difficulties, such as anxiety disorders and depression. And it could globally improve the understanding of autism within the school and in the wider community. And these are some of the de-escalation strategies. And I know at the school I work with, the Oakfield School, there's a hard space, a quiet space, where children often go to if they become overstimulated, or they play games, or they have fidget toys, or they do some exercise. That is the project. I need to put that down because we want to reference. This is a very nice event that we're having in terms of the project at this conference. It involves partners in the UK, Belgium, Bulgaria, and Turkey. 3-year project. There's a project number. Started about a year ago, so we're at the beginning stages. That is the context for what we're doing. We're using machine learning and sensor data, such as the gestures I talked about, to infer when a rumble moment might occur in students with autism, so we can intervene and stave off the intensity and frequency of these types of events. Now, the use of AI machine learning to support students with autism could be seen as contentious in some settings. So I'm going to ask the panel a series of questions, and we want to see whether the contrast in answers between our psychologists and those expert in working with people with autism in comparison with the project members and the technologists here. So my first question would be, what do you see as the ethical issues of using AI in the education of students with autism? Now I can jump in and ask certain people, or would any member of the panel like to shoot away with that question? Carl.
I think that the main ethical issue that pops up is, of course, if you do observations of youth, let's keep it between 6 and 18. That means we do observations on a constant basis in order to understand when is the rumble moment setting in, etc. What is going to happen with this data? I know within the project we have tried to clarify that by saying we We capture data. We don't really care about the person that we capture. We capture data that we then analyze. But for example, parents may object to this. The same, we have discussed that also, is there is a potential application of such solutions also in a working environment, where also, for example, you could predict a potential dangerous situation. That means that actually you observe the whole time in a working environment. So these are issues that either you need complete agreement from the person that is being observed, but then it's also the issue of this person is in an environment with other people there. Do these other people want actually such observation to take place? So this on the one hand, in practice, how you will do that, what are the rules, for example, in the school, what is allowed in the school is very different per country. There are also very specific ethical committees that need to be addressed and need to be contacted. So as a researcher, from a researcher point of view, I would say, okay, we just collect data, we don't take the picture, don't post it anywhere. But when you look at the broader ethical aspect, there are indeed a number of issues that we need to consider. And I'm not an ethics expert, but especially considering that you bring together a number of parameters that actually can point out to identifying a person that you're observing, you're actually touching GDPR aspects directly. So I think there are a lot of challenges that we will have to address by the end of this project, and also any other application domains that we want to consider, because if these are not addressed, it may hamper or it may impact potential exploitation ways. And exploitation here, I obviously mean usage of these technologies in other domains that can be helpful for people with autism, but also other disabilities where a rumble or where at least a distraction aspect is important to guarantee that someone either fully participates in education or that this person has a safe working experience and environment.
Thank you, Carl. That's a very comprehensive answer. Alex, Nadia, as a psychologist, how would you like to respond to any of the points or the questions there?
Sure. Yeah, I think that the main issue. So if you are basically if you are observing children, so presumably via video, in that case, video recordings, you are inevitably going to pick up other children as well. So you have a major issue here in terms of surrounding kids that you might not want to observe, and of course the ethical issues around the parental consent around that. And the other thing is in terms of application for the future. So would you always, in that case, want to have cameras, videos involved in classrooms in order to be able to pick up on these things? So are you going to translate that information on more subtle devices, for example, wearable wristbands that might pick up on physiological changes that can be indicative of the response, in which case the main issue around your video observation, which really compromises anonymity there, I guess, might become less problematic. So what is the long-term strategy here in terms of how do you envisage it long-term to happen in the classroom?
Yeah, basically, Nadia, so we were looking at a range of combining, as we've done in the project together as well, combining, looking at the non-verbal gestures, which is obviously video image, with physiological data as well. So we would be looking at, perhaps we're investigating within the project, the use of, say, a wearable to measure heart rate and heart rate variability. So we'd actually, depending on the context, probably have both sets of sensors. Yeah.
So eventually you can, I'm getting feedback now. So eventually you can, so the video testing phase is only part of the experimental setting, whereas the long-term strategy is a less, a non-anonymous way, whereby just the wearables alone will be indicative of early meltdown. And so I think perhaps you know, this needs to be communicated to parents as well. It needs to be fully understood, right? Because people are always particularly concerned about any pictures, any videos, anything taken in classrooms of their kids. And so schools are concerned about it, parents are concerned about it, and you might find it differs from culture to culture, but I know some cultures are particularly, you know, particularly sensitive about this for various and obvious reasons. So I think the quicker you can move into the wearables, the better it would be from an ethical point of view. I can see how you cannot just completely avoid that, that you have to use the kind of facial expression data to feed into your learning algorithms.
Yeah, I mean, to be honest, it's a really great point you're making, Nadia, that yes, we would be using the video images to train the algorithm, but if it was acceptable in a certain school, depending on the student as well, in a context, we probably would still like to use the real-time functioning of the algorithm to use video data as well. And so, but what you said really brings up an interesting point as well about, you know, perhaps different students, different parents, different contexts, different countries might have different cultures, might have an issue with that. We're trying to make an algorithm which is very flexible. It has a range of sensors, say video sensor, physiological sensor, to be trained on all those sensors, but would still be able to predict and infer meltdown from the available sensors in the particular setting or context. But let's see how far we get with that. Nikki, do you want to, you're our expert in autism. What are your feelings at this point from what you're seeing?
My main concern would be that autistic children tend to already not fit in and be singled out, and by wearing technologies, they might automatically be distinguishable from the other students, which may have unintended consequences. So whether or not you'd take any measures to stop them standing out any more than they already do, because that could obviously lead to them being targeted or bullying for using technology and being sort of identifiable. Quite a lot of children don't disclose, for example.
Yeah, that is a great point. We've actually talked to young people with autism about who would find it acceptable to wear the wearables and who not. And actually we got about a 50-50 split. So I think it's on a case-by-case basis. But yes, you know, the research that we presented just earlier there does show that 71% of students with autism do attend inclusive settings, and the potential for the technology to mark them out is as other and different is something that we, again, ethically, we have to pay good attention to. It's a great point.
Yeah, I think with the Human Rights Act as well, with the right to having a private and family life might be a bit of an issue. I think it would be critical if they understood the potential social implications, because they might not be able to work those out for themselves. So that might have to be they might need to have some education around what could potentially happen so they can make an informed decision.
Yeah. Fantastic. Alex, do you want to come in at all, or any of the technologies?
One of the things I think we might need to be aware of, particularly at the beginning of the project with the video cameras, etc., is the experimenter effect. And so how the knowledge of being under observation might change the behavior of not only the student with autism, but as was mentioned earlier, those students around that person and how that might impact on their behavior. And so we might want to consider how we might address that.
Yeah. So Alex, are you talking about, say, when the student is using the system, that they're aware that they're, you know, actually this came up in a previous project as well. So it's a great point, Alex, that there was that exact effect. Are the students going to behave differently because they know that they're being observed? And, you know, whether we're doing that to judge their engagement or their behavior, the system itself and their knowledge that they're being observed might affect their behavior. I think when we questioned teachers in the previous project and we did some form of thematic analysis, that was one of the issues, one of the themes that arise.
Yeah, one of the ways you might get around that, because the issue there is that children will need to be to consent or have their parents consent to be recorded, so they will know that at some point they're being recorded, but you might not necessarily say when, and so there might be some hidden camera might be there and switched on or off, etc. One of the issues with that, as I mentioned, will not necessarily be the student with autism, but the other students around them, and so when students want to perform, sometimes they perform badly, and so that might in fact increase the risk of bullying behavior.
Yeah. Mufti or Shamin, do you want to make any points coming from the very technical machine learning perspective?
Shamin, go ahead, then I'll come.
Okay. So actually, I would like to, before saying anything, I would like to share one thing. We have a school inside my university, which is actually for autistic children. So there are 19 students in that school, and there are 9 teachers who, teach them inside the school. Recently, they have, posted a notice like they need a male person so that they can manage them inside the school, because the 9 faculty members are female, so they need one male person who can actually handle if there is any kind of and moreover, around the school there are ponds. So the parents want actually one thing, they would like to know their children are safe inside the school, and they are improving their learning ability inside the school. So we know that, for machine learning, for developing any kind of machine learning model, we need to collect, the physiological data, let's say the video data, and we are collecting this data for actually the management purpose. Let's say for ensuring safety and for monitoring, their learning ability. Let's say, their, status is actually improving or decreasing. So we are doing for this. If the parents are happy with this one, in that case, the ethical issue will not be the main point. From our context, actually, from the Bangladeshi context, because everyone has the right to, they get the power of learning, right? And a person will feel valued, honored, empowered if they have the learning. So that's why actually I think the ethical issue is not the main thing over here if the parent is consented.
Thank you, Shaman. Mufti, did you want to go?
So yeah, well, from the technological perspective, I think that the ethical concern remains on whether the developer of the technology who is working on it is really deviating from what the data is meant for. So, for example, that though the data are mostly anonymized and the personal information are removed towards building the model when the data are used in building the model. However, there still remains this chance that during the development process, if the developer wants, they can actually use the physiological data or the sensitive data which are out there to, let's say, identify the person that from whom the data are coming. So that is something which remains, let's say, a major concern in many of the cases whenever, for example, any ethical approval is sought. So this is something as a feedback that we received, that the developer who is working with the data are not going to deliberately try to identify from whom this data is coming. So that is something from the technological perspective is a challenge that, well, the developer needs to be aware of what are the specific, let's say, allowed things that they can perform, and that they should not go beyond those specific objectives that they are trying to achieve using the data in hand. So in my opinion, that is something which is a major ethical issue, yeah, but well, the only way to deal with it probably would be to raise awareness among the developers or among the users of the data who are trying to deal with it.
Thank you, Mufti. I mean, some of the other things that there's an issue, isn't there, with constantly measuring, I think it's performativity. So I don't know if Nadia and Alex are aware of that in education, where you constantly are analyzing and using surveillance on students. And, you know, if, you know, in my job, if I was using AI to look at whether students are engaged or not, I'm never engaged myself all day, and neither would I want to be, really. You have to have time, say, for reflection and doing other things. And this obsession around whether students are engaged for the whole 8 hours while they're there. Well, who amongst us are engaged all the time? And is it really something we really want? Should we be engaged all the time? I don't know if anybody wants to bring that in as well.
Yeah. And in fact, physiologically, we are designed not to be engaged all the time. We have various physiological rhythms. We're familiar with our day and night cycle, which obviously we're disengaged during the night, but during the day we also have a 90-minute cycle, which is waxing and waning of our ability to engage and attend. So we need downtime as well as uptime, really.
Yeah. And I think you know, I can certainly see the rationale that we want to understand when students are engaged, so that if they do become less engaged, we can intervene with other strategies to engage them and look at deep learning. There is, you know, this whole issue around none of us are engaged 24 hours a day, and as you said, Alex, and we have to kind of balance the system between those two competing demands. Another issue that some other educational people said to me as well is, I showed them a previous system we developed. So the system determined, say, for students with learning disabilities and autism, and it had 3 states. It determined whether they're engaged, bored, or frustrated. And I showed this to an educational researcher who was expert in autism. And she said that's hugely over reductionist. And, you know, you could get, you know, it has to be much more subtle and a much more nuanced intervention model. Is there a danger from the psychologist or from Nikki of reducing a student's state into just those 3 categories, do you think?
Sorry, just turning my mic.
Yeah.
You've missed out sensory. A lot of the triggers for meltdowns in autistic people are sensory, so it'll be a reaction to the sensory environment. So it's kind of an overload, short fuse sort of reaction, but also they can be triggered by social overload as well. So tend not to be boredom, but the other confound will be that autistic people tend to learn differently as well. So sometimes you have to employ different learning strategies. So it is really quite complicated, and you can't really apply the same sort of understanding that you would use for a non-autistic child to an autistic child's behaviour, because they do diverge quite significantly in some areas.
Thank you, Nikki. Okay. So that's question 1. We can move now on to question 2, I think. Do you foresee any security issues? I'm laughing really because obviously we do.
Because Carol probably wants to comment something. Yeah.
Okay, Carl, please. I
Whether
can't
we
see
like it or
you.
not, in most US, UK, and also European school, increasingly there is surveillance systems in all the classrooms. Think also actually, I mean, there are people that are against that, but actually if you organize an online training, especially with the pandemic, this was the case, everyone was on a video screen, in fact. So this is a kind of a modus vivendi, a way of working that you see more and more popping up in schools, whether we like it or not. One of the steps could be actually because, okay, there is a surveillance that they say we only use it when something went wrong to see what went wrong. And I think this is a good policy. On the other hand, think a little bit further, and that would mean we have a feed, and if our algorithm works very well, we could recognize why did this person go in such specific state. You said before, okay, there are sensory environments, there are social overloads, and etc. But it's not always clear in a school that has no such experience whatsoever, why did this happen? They don't always know. For example, situation is very simple. Schools are forced into the inclusive education stream, and whether they like it or not, they get students in their classroom with autism. They are not prepared for it, and they don't have a clue when something goes wrong, what caused it. So there is the negative part. Yes, there is surveillance. Yes, we record. On the other hand, it could actually work also beneficially for teachers, for students to see what caused it. We recognize it, what happened. We see how it came up, and hopefully we can also connect it to a specific activity or a specific aspect that happened in the environment. Think, for example, also in some classes, they use very hellish, very bright colors on the walls. And then sometimes they put lights on, LED lights. I have, for example, someone who has a migraine. I go off in less than 2 minutes. In less than 2 minutes, I get a full migraine attack. This is something when you see this on a camera, you see what is happening, you see the light goes on, you see how the student is acting. This is, for example, one practical way of such technology, how we can actually help students, because it's not always clear, especially with younger students, it's not always clear. So understand my intervention here more as, look, you have this on the one side that maybe you do not agree, but on the other hand, it offers potentials. And I would like to highlight again, camera supervision is more and more being tolerated in schools and etc. So while we may have ethical issues with it, more and more schools have less ethical issues with it.
Thank you, Carl. Does anybody else foresee any other types of security issues?
David, can I make a comment on that?
Arif, please go ahead. Yes, thank you.
Okay, thank you, David, for bringing this very general, but it's a very key question in this domain of research. Well, security, what I understand, it's a very diverse one, the diverse term, and we need to think about so many kinds of security, because whenever we are talking in these melting down moment or observing the students, their special need, there are so many ways that can be, there are so many things that can make a big question about the security issue. Like whenever we are capturing data, okay, wherever we are storing that, where we are storing that, okay, that could be a security issue. Then again, we are trying some mathematical model or machine learning model. And in practice, if you are thinking about a personalized a model, so definitely we will think about go in field practice. Then again, there might be a security issue there, because whenever we are exploring that, whenever we are going to implement that, there might have some security issue. So it is, to me, actually, the security issue is a very diverse one, and there are so many stages, at least I can point out 4 or 5 many stages where we need to think about, and we really should care about the security issue and then proceed forward. Thank you very much.
Thank you, Arif. So we've had a range of technology people coming in to immediately see what the security issues are. From the psychology point of view, or Nikki's point of view as an expert in autism, do you see any security issues?
I think provided that the data was just being used, as I think was said before, for the purposes of the study, I can't foresee any security issues that are really obvious. Sorry.
Okay. Okay, thank you, Nikki. Alex or Nadia?
I think one of the things that was raised before was with regards to disclosure of identity, both of the student with autism and those in the classroom. So we would need to protect that.
Yeah, that's a good point. And whether any student could be identified via any attacks or leakages of the training data, which we wouldn't want to happen. So that's a very good point, Alex, that you're using. Obviously, we'll have a lot of training data, some of which will be very visual, camera-based training data, and we'd have to be attend very securely to the security of that kind of data, that can't be used to identify any of the students. From my perspective, when I'm filling in ethics forms from university, usually what we all say is, after a certain amount of time, the data will be destroyed. Whereas actually in machine learning, you don't really want to destroy those data. You want to keep the data very securely, but to keep on training the algorithm and adding extra data into your training base, but keeping all of the data. And actually, it started to change my answers when I'm doing those ethics questions. And I had to talk to our data management officer at Trent. And we both agreed that was a change in the traditional answers we give in ethics applications. We don't actually want to destroy this data. We want to keep it securely, but for a long period of time to keep on training the algorithms. And that was one of the issues that became relevant for me as well.
True, and we probably want to keep it intact as well. So that is going to limit the way that we can obscure the identities of the people being observed, because you've got both the visual and the audio as well. So you'll have the sounds surrounding the student with autism, which will be and in some cases other students' voices, comments, etc.
Yeah, exactly. We don't really want to. We wouldn't be doing anything to the image data to hide the identity of that student, because part of their facial features might be very useful in terms of training the algorithm. Yeah. Any other points?
Well, I suppose one thing is, again, that you're recording other people around. So one thing you can do, even if you keep the data of the individual, and they would have to obviously agree with that keeping of the data, and your research data management plan will have to outline how exactly you keep it secure and across countries as well. So that's the other thing, isn't it? You're dealing with different places, so which might add another level of complexity to it. But people that are recorded externally or in the surroundings, perhaps you'd have to think of a way how you get rid of that, to avoid the kind of, how you only literally are able to keep data from the individual you're looking at, from the participant itself, rather than others around, I guess. Again, just bringing in the notion of the issue that if you're in a classroom, you're recording everyone.
Yeah, and in the past, Nadia, it's been very painstaking to clean up a set of image data to remove the background or other people or other noises. It takes a huge amount of pre-processing work.
Time and money.
Time and money to clean up a set of data examples before you feed it to the algorithm. Yeah, I know that in previous projects, this is something we struggled with. If we've got data, trained examples of, say, facial features of students, which are annotated, then how do you securely transport them back to a central computer to train the algorithm, such as a high-performance computer? And we've investigated many ways to do this. I think at the moment, NTU has a secure data store, which we use for sensitive data like this, but it's a challenge. I don't think I'm going to say publicly, whilst being recorded, how we've managed that in various projects in the past, some very big projects, but it's always a challenge.
I think once the data is in your secure server, you're fine, but it's how it's getting there, right? And how it's getting there from
precisely, yeah,
all the places in a safe and secure way. That's probably the biggest hurdle.
It is. Mufti, did you make a comment here, or would you like to make a comment?
Yeah, well, that is what I was actually, the point that Nadia just touched upon. Well, how the data is coming is something which is quite important in this particular case. Yeah, well, we can, let's say, segregate the data based on the part of the data which is, let's say, which contains the confidential information such as the voice, the video, and other things. And then we can also have the data from where the identity have been removed, the data have been anonymized, and all these things. But how eventually the data is arriving from the source to the destination is something which is always challenging, and we consider that the cloud environments are inherently secure. But well, before we get into the cloud, so there could be a number of places where there might be the risk of data breaching and other things during that particular process. And I invite Shamim also to comment on this.
Thank you, Mufti. Actually, I mean, if we are talking about the data security, we know that the machine learning model itself is susceptible to any kind of security threats or attack, because I mean, any attacker can design some kind of model which will do some kind of drifting in the data collection. And also there was an inversion attack on the machine learning model. So actually, for Mufti already mentioned about the encryption, anonymization technique. So other than this, actually holochain can be used to, ensure the security of the data, so that we can, the data are arriving at the destination from the authentic source. It can be ensured if we can have any kind of distributed security measure like holochain or blockchain. And yeah, that's it.
Yeah, that's a really important point you just raised there, Shaman. Excuse me. The potential use of blockchain to enhance security in a system like this, I think, is becoming increasingly important, and it, is offering increasing utility to improve the security in a system like that. So, thank you for mentioning blockchain.
Just as a slight aside to this, and linking back to question 1, David, is the application of these methods once, and I think this was broached earlier on, but there is, in terms of, for example, teachers using such tools, a need for them to realize that machines can also make mistakes, and not to ignore their own senses and their own sensibilities. So relying fully on the AI to detect things rather than to be aware of them themselves and to respond appropriately.
Excellent. Alex, and you've reminded me of something else there, so thank you for bringing that up. I was talking to some teachers in special schools, and they were saying, well, you might have a very, very experienced teacher who is aware of that particular student, and the prediction of the algorithm could augment their decision, their reasoning about whether the child's engaged or approaching a meltdown event. But then you might have a very inexperienced teaching assistant who comes along, sees the output from the algorithm and just goes with that. And apparently in the UK, the level of training given to teaching assistants and their experience and expertise varies greatly. So if they just see the outcome of the system like this, or the child's going to have a meltdown, or they're not engaged to do something, and they completely go and believe the system, can end up with anything from bad teaching practice to more serious consequences. So it has to be that kind of ethical vision, doesn't it? That the use of AI is here to support teachers to make decisions, but it can't dictate decisions. And we have to realize that in terms of a community of practice, we're going to go from very experienced teachers to very new, fresh, and inexperienced teaching assistants, for instance. And there has to be some framework, some ethical framework, which allows the use of the introduction of AI in education, so that it's supporting best practice and supporting the needs of the students, rather than an example that was given to me is a very fresh or new, inexperienced TA could come along, see the output of the system, and then just saying, not really understanding the complexity of the teacher-human interaction.
So I guess it's all in the communication, right? And how it's being communicated to the teachers in terms of how to use it and its best practice, and maybe raising the understanding of things like, false negatives, false positives, and how any machine, just as any human, can have errorsome outputs. And so it's the right communication around it that becomes really vital, how to explain it best, and training, right? It's all about the training in the end. The teachers need to be just as well trained to understand the machines as they should be, well trained how to understand what autism is in school. And you're quite right, unfortunately, the training isn't always there. We have this great concept of inclusion and inclusive school settings, but teachers don't always get the level of training to understand neurodiversity and how to best support them. And Nikki is probably the best one to talk about that aspect. But it's a huge problem because it's not part of standard curriculum.
Just to add a little bit to what just Nadia mentioned, well, the problem even gets more aggravated when we move into machine learning, because you see, machine learning is inherently based on what we actually showed before, which means that the training data. So it is, let's say that somehow the biasness of the data is something which also plays a very important role. For example, let's say that if we train an algorithm on, let's say, data coming from a particular population only, if some other populations, children or some specific race or something, that the data is trained the methods or model on, if there are some other people who are coming to that particular model or they are exposed to that particular model, the model tends to perform very poorly. And this is something which is very, very well known. And this is in case of, let's say, autism is a very big problem, because first of all, we have very limited data. And then we actually do not know very often times that, well, which kind of specific autism that we are dealing with, because it is a spectrum. So not that if we put everything on a single pot, might be we are doing a big mistake. So there is this always risk that what we are training the model with is probably we are letting the model to recognize something which otherwise is very wrong.
Thank you, Mufti.
I think you're adding to the complexity here as well in terms of facial expressions, for example, which are very culturally normative and different from culture to culture, right? So the recognition of facial expressions and the meaning of facial expressions can vary in different cultures. And so presumably, I mean, you know, you have to train your model in a way that it recognizes that depending on where it's being put in use. And so it's good that you already do it cross-culturally, because, you know, you can't just develop a model like this in the UK and expect it to work everywhere, because it won't.
Yeah, it's a great point, Nadia. We have a European project, but we also have, between our university, computer science, psychology, we have our link to Bangladesh and to India, with Sherman involved in several projects with us. So, and I think that's, you know, that's a strength of the project, but it's a great point. I might just want to ask the machine learning people here, you know, we do have, it's a very heterogeneous population, as you just said, and then there's different cultural differences as well. What are the machine learning potentials to cope with that very heterogeneous population? Transfer learning, one-shot learning? You tell me.
Yeah, well, so if I just bring it onto the table, so then we can have definitely further discussions on that. So, for example, people have been talking about many different types of learning when it comes to the video data. However, well, when we think of recognition of specific subtle patterns in the video data, actually most of the times these, for example, one-shot learning or even zero-shot learning, which appears to be very successful in certain applications, in this particular specific applications, they do not seem to perform very well. So this is one of the things that, well, one-shot learning is that yes, please. Yes, please.
I was just going to say, isn't zero-shot learning just unsupervised learning?
Well, there is a dispute between that whether it should be termed as unsupervised, but well, some of the people, they term it as supervised as well.
Okay.
So from that particular perspective, well, there is a convolutional neural network, but the difficulty is that with the convolutional neural network, we need huge amount of data. Now, in case of the autism, as we are dealing with people, and Shamim, who has vast experience in getting data from autistic children in a school, okay, so he will be able to comment more on the heterogeneity of the different behavior that he saw when collecting data from the students. So that is something which is yet another challenge that, well, we are planning to use, let's say, specific machine learning techniques which requires a large amount of data, but then we are restricted by the amount of data that we can attribute to one specific type of autism. So that is the data scarcity is one big issue. And then then we have certain patterns. Definitely, for example, the recurrent neural network based certain models, okay, like LSTM or attention based LSTM, which have shown their potential in trying to predict time series data with somewhat good accuracy. However, well, again, what we lack here is the data which is coming from the autistic cohort. That is, the main reason is being that from our experience, it appeared that many of the autistic children, they do not want to be putting on any smart watches or anything on their body. So that is something which has been yet another challenge. So from that particular perspective, yeah, well, there are a number of let's say ways that we can approach the problem. For example, the easiest way is probably to use of AI in inclusive education, in the sense, try to provide the students some learning material based on their interaction. Okay, so how and which kind of materials that they're interacting with. So can we provide a little bit more on that particular material, or can we really provide them that flexibility for them to engage more with similar kind of material and try to see that how they're interacting those. So that is something which does not necessarily require, let's say, personalized data which is recorded and which is type specific to the autism. We can probably say that a number of techniques, for example, the LSTM based neural networks or a simple fuzzy based system also can be employed in building that personalized tutoring experience. So that is somewhere I think that right now we can very easily utilize the existing AI-based methods that we have in hands.
Thank you, Mufti. That's a great answer in terms of how advanced machine learning can really start to at least tackle the problem of this being a very heterogeneous population, cultural differences, and machine learning is evolving to start to face and to start to tackle some of these challenges. I'm going to go to the next question because we're running out of time, and I do want to ask the audience if they want to ask any of the panel members a specific question as well. So last question, and I'm actually going to go to Nikki first on this one. How could AI be successfully used in the classroom to support students with a range of challenges? We thought about creating personalized learning pathways, or inferring challenging behavior. But there may be others. So Nikki, would you like to go first on this one?
I think you could consider using it to monitor anxiety levels, to anticipate things like meltdowns. Also, something that might be interesting would be something like a pain app. If an autistic person is injured, quite often they don't recognize the extent of their own injury because they can have a different pain response. They might not feel the pain, but they can communicate it via an app a lot better. Similarly with emotions, a sort of a way of communicating emotions through an app or through using AI might be useful. Maybe using some of the predictive technology that you've used, if you can kind of link that up to the emotion that they're experiencing based on their facial manifestations.
Brilliant. I think you've just written our next 3 grant applications there, Nikki.
Thank you.
Anybody else want to jump in here?
David, I just want to come back to something you mentioned earlier in terms of the model you might be using, and if it's too reductionist and too simple. Of course, in most cases it is. Emotions are very complex and multifaceted, as we know, and we had discussions around this before. I mean, even in terms of anxiety and fear responses, for example, threat responses. But you were talking about boredom earlier. Boredom sometimes leads to frustration. Frustration sometimes leads to aggression. So you can have a chain of events here that can trigger an emotional response in a way you might not anticipate. So you might think boredom is maybe not so relevant, but I think the more fine-tuned one can be, the better it is. But the physiological response, I mean, in terms of heart rate variability, for example, is there. So we know, if there's an increase, then there might be a potential for something. And Nikki's suggestion about the feedback of emotion perceived in the autistic individual might be really good, because we might infer an emotional response that they might perceive very differently. And in a similar vein here, I can say, so for example, if we're looking at individuals with alexithymia, they might have an emotional response, but they really struggle labeling it, right? And so you're suddenly looking at a very, very different issue there, that again, that labeling might be different or might be atypical. So perhaps thinking about not just about recognizing an emotional response, but how does the individual actually perceive that emotional response can become really important. And the more fine-tuned you can be there, the better it will probably be, because whatever we think in a typical way of how we might respond might not always apply in the same way. So I think Nikki made a very good point there as well.
That's a great point. Nikki, we have another project which we're hoping to extend. It was called the Internet of Soft Things. So people co-created smart textile objects, but they put things like lights and switches in those. And then they, rather than just saying, I feel like this, which a lot of people were challenged to do, they communicated their emotions by sending almost like how they interacted with their thing to send a message to somebody else at a distance. And that's how they were communicating how they felt.
There's something systemizing. So I don't know if you've read Simon Baron-Cohen's empathizing systemizing theory, and what you can do. No, autistic people are supposed to be very good at understanding systems and systemizing. The bit about empathy is really contentious and I don't like it. But the systemizing bits, they tend to be very adept. So if you can use a way of communicating emotion by using something that uses systems like your soft toys that you described, then that's often really effective. So that's actually a practical application of that theory.
No, that's brilliant. Yeah, I was having a conversation about assignment to somebody else, which was a bit more contentious, but that sounds very interesting. And that was really the idea. We weren't going to use potentially just a spoken language to communicate how you felt. It was very much about you building a thing and using that to communicate how you felt by a gesture or interaction with the thing and via the internet or a local network. So good. Thank you for pointing out that, and I'll read up on that.
David, another thing I might wanted to add to something that was said earlier, and I couldn't quite get it in at the time. So one important point Nikki made was in terms of the sensory overload. So I think any kind of AI system that also monitors external input, not just the person itself and the internal indicators, but the external indicators from noise, temperature, light levels, etc. All of these can additionally feed and or give at least indicators of trigger points that might be really important. And I know Ayman and people are really good with these type of things.
Yeah, because I know that was something the university wanted to do. They wanted to try to understand engagement in different environments for students, so that in a way you could optimize. You would say, well, that's a really nice space for this group of students to work in. But again, that was a bit surveillance-like as well. But it was quite an interesting concept, I thought, as well.
One of the things we're looking at, David, is neurodiversity in the context of biophilic environments. And so those environments that actually incorporate features of nature or nature, how that can impact on well-being. And the other thing I just wanted to raise very, very briefly as well, we started off talking about rumble moments. And then very interestingly, Nikki started talking about emotions as a wider spectrum. And I think this is really important because as well as the rumble moments, we want to know when students with autism are feeling happy, are feeling rewarded, are feeling motivated, are feeling engaged. And so I think those types of positive emotions are equally important as identifying the rumble moments as well.
Yeah, absolutely. I suppose I concentrated on the rumble moments, and we are using machine learning to also infer engagement, but the wider spectrum of emotions, and I know I've worked with this with Nadia, is also something very important and something that we're looking to do in a future project, building on the work that we did on an Internet of Soft Things. How do you express emotion potentially at a distance via something you build, which might be suited to the way that students with autism might identify their own emotions and choose to communicate them, is something that we're working towards. And it would have to be a system which allowed the young people to express a whole range of emotions. First of all, to understand what their emotions were, and then to communicate via either gesture or interaction or some other way of communicating at a distance. Not just because well, you might want to do that at a distance for people with autism, but just a lot of opportunity for young people at the moment is closed down in terms of meeting perhaps as many times as you'd want to. So how can kind of an Internet of Things approach benefit students if they are restricted in how many times they can meet up with their friends due to a number of reasons? Does anybody else want to chip in before I offer the floor to the rest of the observers here? Do any other members of the panel want to identify how AI could be used in the classroom and other opportunities? Shaman, you've got your hand up.
Yeah. David, in my opinion, AI could be successfully used in classroom if we use human factor, let's say pedagogical design, AI, as well as teacher experience. If we combine all these things together, in that case, AI could be successfully used in classroom. And we know that these four components, the AI, pedagogical design, human factors, as well as the expert opinion, we use these things for designing game for, understanding people's behavior. So if we combine this, all these things in the classroom, in this case, actually, AI could be successful. Thank you.
Shaman, that's carry on. Sorry, Nadia. Sorry.
May I add to that? Sorry, I'm just thinking here in the context of Julia's PhD on interpersonal coordination, for example, right? So we know that sometimes synchrony, interpersonal synchrony might have a positive effect on therapeutic alliance between a client and a therapist, right? We don't know quite exactly how it would work maybe in terms of autism, but because you're really pertaining here to the dynamics in the classroom between the teacher, and it's not just about the individual, is what happens around the individual and who it happens with, and how these kind of interpersonal dynamics between two or more people might also influence the emotional affective state of the individual. Just to add on this, to make it even more complex. There you go.
David, can I add something, please?
Of course you can. Please go ahead.
Many of the points have already been pointed out, but I want to just go one step backwards. So as far as AI or ML is concerned, three things ML can do really, really good. One is prediction, one is clustering, and one is the classification. Okay, so whenever we are talking about these classroom activity, and in terms of classroom activity, if we can actually split the focus in terms of these three things, then we can actually focus it down even further. Okay, then there is two more ways. One is you can say as an aggregate form or in personalized pathway. Machine learning can actually work in both directions. So if we can actually focus our point, actually what we want to do and how we want to do, perhaps there is a way. As my background is with machine learning, so I'm kind of confident that if we, let's say we want to predict something and in a personalized form, okay, and we explore through the sensor data or whatever type of data, perhaps we can actually go to a certain level when we can predict something. Perhaps there will have some mistakes or there will have some error, but we can actually evaluate them in terms of what type of machine learning model we are using. Okay, so definitely I'm kind of optimistic that ML or machine learning, it can actually help us a lot, but we need to really know what we actually want. So it's both of the domain are very diverse. Like dealing with the autistic is really, really, even as a human, we struggle a lot. Again, the machine learning itself a diverse domain. So when you are actually bringing these two diverse domain in one point, we need to focus our point, actually what we want. Okay, if we can focus it narrowly, perhaps we can actually reach a point. Yeah, thank you.
And it's a good point, and they're the conversations we're having. Just as a point of information, we held monthly meetings of groups of young students with learning disabilities, young adults with learning disabilities and autism, with their teachers, parents, and carers. It's called the NICER group. We're next meeting on the 23rd of September. It's really, I invite, and that also includes psychologists from Nottingham City Council. So, it's been a great conversation today, and I'd invite the people here to come along to those meetings, so that the technologists can be informed by the young people themselves and their parents and teachers as well as people working in professional services too. That's been a fantastically informed, well-informed and interesting conversation. And first of all, before I open up the floor, I'd really like to thank Nikki, Nadia and Alex for joining us today, along with Carl and Mufti and Shaman and Arif. It's been, I know, giving up your time. You're all organizing other conferences at the moment, and I know your time is incredibly precious. So thank you for that time. So before we go and thank the panel members, are there any other questions that the general audience wants to ask either one of the panel or all of the panel members?
Actually, I would like to point out here that among the audience, there is Dr. Marina Minoli, who has quite extensive experience in science education and its connection to human behavior. But unfortunately, I see that she does not have the audio enabled. So otherwise, well, it would have been very good to have some comment from her side.
Okay, that's a shame. Okay. Any other questions from the general audience at all? And if there is somebody I can't see, Mufti, you might want to point it out to me as well. Because I could stop sharing my screen so that I could do that, yes.
I think Professor Shahadat is here. He's actually working with the AI Enable. Professor Shahadat, are you here? I think he can suggest something. Yeah.
I'll mute.
So I would be happy to know in which area that is you are seeking my suggestions. In the classroom environment?
Yeah. Classroom environment and security, you can just comment. I mean, if you would like to add something.
Yeah. Actually, I would like to see artificial intelligence in a very different way. Actually, in order to understand, that is, we need to understand why we have a natural things and we have artificial things. Now the point is that why the conversion of natural things into artificial things is necessary. If you have a look at first industrial revolution, basically we have converted energy using the steam engine, for example. So the birthplace of first industrial revolution is the Manchester. And likewise, now we have natural intelligence, and we would like to convert the natural intelligence into artificial intelligence. Say, for example, this conference, I should say, it's not natural way of doing the conference, but it's an artificial way of doing the conference. But the benefits of converting the natural into artificial, in my view, we have three types of benefits. That is, the things become cheap. That is, you can produce abundance, and then at the same time, quality can be ensured. So organizing this type of conference, for example, that is now we are abundance of conference throughout the world, but at the same time it's also very high. So in the classroom environment, if we look at the classroom environment in this way, now we are talking about the online education, especially it's become now reality during this pandemic, especially if we take the example of Bangladesh. So I myself also involved in implementing this type of education at the grassroots level of Bangladesh in so many universities. What I have seen that the motivations, the learning of the students in the classroom environment is really amazing and high. So I can cite an example. Say, for example, in one of the class, when there is a physical environment, usually 15 students out of 50, they remain present. But when they used to in the artificial environment, their present improved tremendously. It is from 15 to 35 and 40. So I think there is a good benefit of using artificial intelligence technique in the classroom environment. So at this point, I would like to add two things. That is, now we need to have the citizenship in the true world. One is the physical world, and another is the artificial world. The intensity, if you can increase in the artificial world in terms of your citizenship, I think this will be a huge benefit, because every time now we are creating the digital footprint, as you know. So I would like to see the use of artificial intelligence in this way in the classroom environment. Thank you very much for giving me the floor.
Yes, thank you very much for that as well. Which that reminds, I went to the House of Commons inquiry into the use of AI in education, and most of the MPs there were asking me whether it would save them money. The use of AI in education, and I kept saying, no, it's there to augment teaching practice, not to replace the teachers. And then when I said that, they kept losing interest. There you go. Well, I just want to thank the panel members again and all the audience. This has been an incredibly interesting and lively discussion, but really informative as well. With everyone's permission, we're going to look at some of the answers and afterwards, because what we're really interested in is having a shared vision of the ethical use of AI in education, especially for students who perhaps have not always enjoyed the advantages of enabling technologies. So we'll be in touch with everybody after the panel. Okay, I want to draw things to a close now. Thanks to Mufti and Shamin for organizing this session, and thanks to all the panel members.
Thank you very much.
Thank you very much, David.
Bye-bye.
Thank you very much.
Thank you. Bye.
Bye-bye.
A photo. Just wait a minute.
Okay. Yes.
Done. Thank you.
Yeah, bye-bye.
So easy to organize group photos these days.
Bye-bye.
Take care. Bye-bye. Bye-bye, everybody. Bye-bye.
Bye-bye.
Mufti, are you ready for next Wednesday?
Yes, I'm getting ready for next Wednesday. Thank you very much for the opportunity. I really appreciate it. Well, it has been a little bit difficult with the organization of this conference, but now that it's coming a close, so just a second, let me just stop the broadcasting to YouTube.